So good morning. My name is Federico Isidro. I'm a PhD student at the José María and Carlos Oscarla. Focused mainly on algorithms, integration, and development. And this first session is going to be driven by my colleague José Luis Vilas and myself. And in this first session, we are going to go through the very raw data that goes out from the microscope to the final tomogram reconstruction. And I will let the things open for the days coming on. So if everyone is okay, we start. So I prepared a very first introduction. Of course, if I'm going too fast, please let me know. So I prepared an introduction. I know that some of you have more experience on tomography and some of you have something less experience. So I tried to make a brief introduction just to everyone catch up and be all of us in the same page. And finish the introduction that I promise it will be short. We will have two sessions, one in the morning, one in the evening. The first one is going to be driven by myself. We are going to go through the tilt series alignment and tomogram reconstruction. We are going to go through both manual and automatic tools. And in the second session, we will go into the CTF estimation and correction in tomography and reconstructions considering the effects of the CTF. And that will be driven by Jose Luis. So I think you can see my pointer. Yeah, I think you can see. So let's start with introduction. So as in SPA, which maybe some of you are more familiar with, we are going to study some biological samples that are going to be embedded in an edge layer. And these samples in tomography may vary. We shall study cellular complexes, membrane proteins in vesicles, even some purified specimens or proteins, as in SPA. And the difference, or the main difference between SPA, is that in this case, we are going to have projective information of our sample from different points of view. And we will go in later on that, but this is very interesting, mainly for several reasons, but one of them that I will introduce now is that we are able to have 3D reconstructions of single targets. That this is something that breaks with the previous SPA approach. And this is this is because since we have information of the same target, the same particle, the same protein through different views, we can combine this information into a 3D reconstruction. And well, this set of images, this set of projections, it's what we call tilt series. Okay, each tilt series, the tilt series are composed by a set of tilt images that are taken at different tilt angles. So I'm not going to go into details. This is more an algorithm course, but I will go. Well, we'll try to make a brief introduction of the technique. So as I said, we have our sample embedded in ice. The devices here are most similar to what you may know from single particle analysis, and the main difference comes comes in this kind of pipe, which is an arm holder, that is responsible of rotating the sample. And this rotation of the sample is what gives us information from the different perspectives, right? So basically, the device is almost the same. We are going to radiate our sample with the electrons and recover the information of how these electrons are affected by the sample they are going through. And due to the design of this, and this is something that we will have to deal with through all the processing in tomography, due to how this arm works, we cannot have information from all the perspectives. Think maybe about X-ray tomography in medicine, in the hospitals, where you can have information from all the directions. Here, because of how the arm is constructed, there are some angles that we do not have access to. And although this may look something not that much important, actually it is because this section of perspectives that we won't have access to, it's going to generate some artifacts. This is what we call the missing wedge, which is basically those regions from which we do not have perspective information, projective information. I like very much this image because I think it's very illustrative. Mainly because what we can see from here is that, well, first of all, we are affected by the missing wedge, but we are also affected by this angular sampling of the series. So here we have a trade-off. We have a compromise between which is the resolution, or which is the number of perspectives that we are going to consider, and how much we are going to radiate our sample. So we cannot commit only to one objective. We have to do a trade-off between both. And between the angular sampling and the missing wedge, our sample is going to be affected. So for example, here you have what would be the original image, a perfect reconstruction with a very high angular sampling and a non-missing wedge. But as you can see, if you increase the missing wedge, or you reduce the sampling of the angular sampling, the results will deteriorate. And we will go through this, and you will have the chance to see it. But the artifacts generated by the missing wedge are very peculiar and may driven our algorithm. So this is some effect or some artifact that we will have to deal with, and we will have to consider through all the processing. Just last comment, we are not going to go through this in this course, but maybe some of you have previous experience and you heard about this dual axis acquisition, where you have the same sample, and instead of rotating in one direction, you rotate it with one axis, you rotate it with two axes. And in that case, instead of a wedge, you would have kind of a missing pyramid. But as I said, this is not going to be covered. And the advantage of this is that effects of the missing wedge will be reduced. And just the end of the introduction, and we'll start with hands-on things. We are going to, or I'm going to present a little bit overview of the workflow for this first day. And well, as I said, this idea of acquiring images of different tilts at different projective directions, it's basically used, or our objective is to combine this projective information into a 3D reconstruction. And this is the main, or the aim of this first session. Then the pipeline then kinds of open, and tomography is maybe not as a closed pipeline as it could be in single particle analysis. But this 3D reconstruction is, I don't want to say straightforward, but it's more closed and than maybe the posterior steps that you will see in the days going on. And well, as I said, this combination of 2D information into a 3D reconstruction requires of some pre-process, or taking some steps before reaching the tomogram. It's not something straightforward. We need to work with our T series to posteriorly get a 3D reconstruction. One of the main things it's that images must be aligned. If images are not, we won't have a 3D reconstruction that we are able to use. So this is a core step. And as a sum up, as in single particle analysis, we will have some movies. We are going to work both with movies and directly with the T series. And there are like two branches that opens and combines at the end, or might combine at the end. The first branch goes into the preprocessing and alignment of the series. We are going to perform some steps of preprocessing, like removing the X-ray artifacts and those filtering the images, some process of resampling, to posteriorly align the image. All the data that we are going to work with have gold bits, have fiducial markers. We will see what it is. And this might end directly with the tomogram reconstruction. But there is another branch that opened, which is according to the CTF, which is going to be the second session of today, which starts with CTF estimation and correction. And we can use this image combined with the alignment in order to get a final tomogram reconstruction, or even better, we can have a tomogram reconstructed, but considering the effects of the CTF in the 3D space. And well, just a close-up. As I said, we are going to go through the whole reconstruction step from raw images to our final tomogram. And once we have this 3D reconstruction, which is the object, the aim of today, there are several things that might open up. This is content for the following days, but we can go maybe for segmentation if we are more interested in the cellular macro view of the sample. We can go to subtomogram averaging, which is basically pick those objects that we are interested in and classify them through their shape. And a newer approach of what is called per particle, which is basically a refinement of these objects going back to the TIL series, refine the volumes from the projective information. So this ends up the introduction. I hope everything is fine. Okay, so I see some of you having problems. Yeah, okay. I actually don't know how to fix it. Yeah, I can close it. Yeah, I'm going to quit this. Sorry for that. I hope. Okay, seems like now disappeared. Okay, sorry guys. Thank you very much. So now I'm going to ask you for, if no one has any further doubt, and if you have no questions, theoretical questions about the first step of the workflow, we are going to go to the machines, and we are going to start working with Sapien directly. So, okay, this is not good. Okay, please let me close this and reopen it again.
Sorry, Fede. I guess they're supposed to follow you when you do you explain the step and then they do the same, right?
I know. It's just that my machine.
Yeah. No, I'm just.
Okay. Thank you, Pablo.
Explaining. Yeah.
Okay, so I'm going to close everything. So this should be something similar to what you see. You have a direct access to Sapien. So you just double click on it and you have this first window. In this first window, basically what you see is the projects that you have in your Sapien environment. You have the chance of importing a previous generated project, maybe another computer, maybe in another Sapien installation, or create a new one. Before creating a new one, let me say that, as you can see, you have, or you might, you should see some pre-created projects. These projects are basically the templates, the executed templates of the following days course. Today we are going to generate this project, and at the end, if everything goes fine and we have no problem, you should have the same thing that is held here, but created by your own. And if any moment you get lost and you don't want to ask, you can go to this project and check the results, copy the parameters. Okay, now opens. So as I said, you should have this at the end of the day. And as I said, if you have any question, you might, and if you get lost in any moment, you might go to this project and check the results or check the execution. So
sorry for that. And apart from that, if you have any problem, you can type the problem you have on the chat, and we're some people from the team that we may help you in the breakout rooms and so on.
Okay. Thank you very much, Fede. He's completely right. So if you have any problem, please, guys, let us know, and we will try to help you out. So we will start from the very beginning. We are going to start creating a project. Just type on create. Let's call it, I mean, whatever you want. I'm gonna call it day 1 project, for example. And this will create in this location. You can change the location. It's something I don't usually do. I want to have all my projects in the project folder, but if for some reason you have any partition or whatever, you can hold it there. And we just click on create. So once the project is created, by default it opens the SPA, but we are going to tomography. So I'm going to do for those of you that might be not familiar with Cypion, I'm going to do a first overview, and then we start with the pre-processing. So please, if you have any doubt about the basics of Cypion or the basics of the workflow, it's a good moment. So Cypion is basically, or the Cypion interface is divided in 3 sections. The project section, which is the big central one, that now it's empty. You don't see anything. Here in the lower part, we have a summary, methods, and output log that are also empty because we haven't executed anything yet. But here just to have some information that sum up the protocol you have selected, the methods that protocol use, and the output log, which is basically all the process that it's run behind, and where if you have any problem with the protocol, is a good source of information. So well, maybe this is not the most visited screen, but it's a lot of information holded here. And finally, in the left part, we have all the protocols that we have integrated in Cypion. We have many plugins, IMOD, Dynamo, CryoEM, xmipp, Bisec. We have EMAN. We have a lot of protocols here. There is another view that maybe is less intuitive, which is all, that shows up all the plugins that you have installed and its protocols. But maybe this is less user-friendly, since we try to make this easier for you to use. I would rather spend most of the time in this sheet. And here we try to condense the tomography workflow, the most intuitive way we think it is, although we are always glad to hear from you if you have any other opinion. But the workflow starts with some imports. We have lots of types of imports for a specific software, for general software. Today we are going to use basically these 2, which are import series and import series movies. But the following days you will use some of the rest. Then we have some tools for going to the T series to the T series movies. I will go in the details later on all these steps, but for you to know. Then we have all the tools related with the T series. With first of all the pre-process I mentioned before, the CTF tools and the alignment tools. And we are going to spend a lot of time here today. And finally, the tomograms. And well, here basically today we are going to be most of the time here in tomogram reconstruction, since it's the end of our workflow. Although we have some other tools of pre-process, We will have a little bit on monotomo today about quality analysis if we have time, but we have some other tools for denoising, segmentation, post-processing tomograms, and then this is where I said that the workflow opens, and well, we have some subtomogram averaging tools for pre-processing, classification, pickings, and extracting particles. So as you can see, there is a lot of protocols, there is a lot of options. And well, today we are going to be focused most of the time here, but through the whole course, you will have time to catch up on all these tools and see how powerful it is and how easy it is to combine different methods. And as a final recall, if you click Control F, this screen, this window will pop up. And this is basically a searcher, which in case you feel a little bit overwhelmed or you have some problems finding some tools, some protocols, it's very easy. So for example, I don't know, today we are going to work a lot with IMOD. So imagine I want to see the protocols for IMOD, but this has a keywords searcher, and it will pop up all the IMOD protocols. Imagine that instead of that, I'm interested only in CTF tools, for example, then I can type CTF. Well, here you will see both. You will see both SPA and tomography methods, but you will see here the methods. So if there is no further doubt, I will start with the workflow. So let's check the chat. Okay, so if there is no questions or everyone is on the same page, we are going to start with the workflow. So first workflow, we are going to do this morning 2 different workflows. The first one is going to be dealing with TIL series and automatic alignment. And in the second one, we are going to deal with TIL series movies and manual tools in detail with the eTomo tool that maybe some of you is familiar with. So please, let's start with importing the T-series. So we are going to, as I said, import T-series, not T-series movies. We could open it here, double click, or you could just Control F it, import TIL, and yes, it should appear, import T-series. And if you double click here, you end up in the same page. So we have prepared 2 data sets. So if you go to data folder, double click, and then you go to day 1, because it's the first day of the course, you are going to see the 2, you will have here the 2 data sets we have, the movies and the T series. So we are going to go to the T series.
Federico?
Yep.
Hi, please. Could you repeat it and go a little slower?
Sure. Okay, sure. No problem.
Thank you.
No problem. Thank you very much. No problem. Okay, so as I said, we imported this series. Okay, this protocol is the only time that you will need to deal with files. Once this information is integrated inside Sapien, the rest of the time you will work with tools held in the environment. Okay. So to import these files, we need to let STPN know where it has to search for them. So here in the files directory, field, we click on this folder, and this window will pop up. Well, here this is a classical browser. This has no secrets for you, I'm sure. And all the data that we are going to work with through the course, it's held here in the data folder. We have some extra data and the data for the following days of the course. So if you go into the day 1 data, which is the data for this first session, you will see the TIL series the T series movies. So for this first workflow, we are going to work with the T series. So we just double click, and this is the folder where all the information is held. So we are going to click here on select. And as you can see, Sapiens completed for you the directories where all these files are located. I'm going to now reopen this to explain you something. There is a lot of ways to importing information inside Sapiens because tomography data, we have seen that varies a lot depending on the sources, how the data has been acquired in the microscope, if it has been pre-processed or not. Maybe someone used motion core and someone used another software, or maybe you want to go directly with some more raw data. So we try to be as extensive as possible on the options that you have for importing data. I can go slower, yes, sure. So we have a bunch of options for importing data, but there are two main blocks of information now that you will need to be aware of. First of all, the tilt information. This is about the angles at which the information has been acquired. And there is a second part, which is the acquisition info, which is basically the configuration of the microscope at which the information has been acquired. This is more similar to SPA, maybe. Here you have the microscope voltage, the magnification, the pixel size, so parameters that also appears in single particle analysis. The dose also, and a new parameter that appears, which is the tilt axis angle, which is basically how our images are rotated through the acquisition process. This will make sense later on that we explain it, but as you can see, there is a lot of information. And also for the tilt information, there are a bunch of ways of importing it. You can import it maybe from a range, because you know that my image has been acquired from this angle to this angle with this step, or maybe you want to read information from a header, or maybe you have the TLT file, which is a text file with all the angles at which our images has been acquired. So there is a lot of options, and this can get a little bit messy. Because of this, what we recommend, in case it's possible, it's to use. Sorry, I think there is a microphone.
Yeah.
Oh, okay, sorry. So since there is a lot of options.
Sorry, I muted when I started to talk. Sorry, Fede. Some people in the chat are requesting you to go a little bit slower.
Okay, I will go slower. Thank you guys for letting me know. And well, as I was saying, all these options can get a little bit messy, as we know, and that's why we recommend to use MDoc files. So I'm going to open an MDoc file just for you to be familiarized with, although you do not have to deal with, but this is a file generated by the microscope when the acquisition it's done, and it holds a lot of information about how many images have been acquired, at which angles, which one is the tilt axis angle, a lot of information. since this information, as I said, can be get messy to go from the MDoc files to the CPM folder, we have developed an option to directly import information from the MDoc files, so you do not have to deal with it. So if you type this, also this pattern field works with all the classical keywords as well as the asterisk and these kind of things. We can directly import the MDoc files, and Sapien will make all the searching files, but also complete the information, and all the information will be held inside Sapien. So you do not need to go directly complete the parameter. So if I tap here asterisk MDoc file, which basically means look for all the MDoc files here and import the data. This MDoc file, this protocol will take the information that we have seen that is contained inside these files, and will introduce or generate Sapien abstractions for this information, so you do not have to deal with it. I know there is sometimes that there is no available MDoc files, and then things might get messy. But in case they are, I really recommend to use it, just because sometimes you might not even type something wrong, but confuse some data because there are fields with a lot of parameters. So I really recommend to use this option. But just in case, for any reason, you want to change some variable, I don't know, maybe imagine that you have some problem with the acquisition of the microscope, some misconfiguration. You can change any of these variables. So this data, for example, have been acquired with a microscope of 300 volts, but I can change the value here, or the pixel size, or whatever. We are not going to do it because our MDocs for this example are fine, but well, this is something that I think is interesting for you to know. So we do not need anything else. We have all our information here. So we just click on execute. So well, I'm going to close this, and we click on execute. And let's give it a couple of seconds. And this Sapien is now reading all the MDocs, generating the files, and the information is completed in our abstractions inside Sapien. So here we have our first finished green box. So, well, first of all, I don't know if anyone reached here. If you have any problem, please let me know. But as you can see, we have our first Sapien object, set of T-series.
Baño, en todos los sitios, vale.
Okay, hello? Okay. So, yeah, I press on execute. Yes, I don't know if there is any further question.
Federico, this is Isai from ESRF. Hi, just a quick question. So you showed for the serial EM acquisition. So I presume it works for EPU as well, but I'm not sure EPU provides a doc file. I think it's an XML file. Will this adapt as well for EPU Tomo, for example?
From now on, we only have methods for reading information from MDoc files. So
okay.
But if you have, I'm personally not familiar with these kind of files, but if you have any example of this, and if you can let us have the file, we might adapt it to these kind of files too. But from now on, yes.
I think, sorry, Fede. I think since MDoc files are quite popular, I've been told, and I think Francisco Javier is also writing in the chat that Thermo Fisher is going to provide MDoc files as well. So if that's the case, then it's covered. Maybe in future versions.
Okay. Thank you.
Otherwise we will implement the whatever file EPU needs or generates.
Okay. Okay. Thanks.
You're welcome. So if everything's fine, okay. So as I was saying, we have finished our first protocol inside Sapien. So congrats, everyone. And as you can see, Sapien has generated a set of the series. A set of the series is basically a set of the series inside our abstraction. Here you can see that we have 3 T series with these dimensions of 41 image and with this pixel size. So as I said, only providing the MDoc, Sapien has completed all the information for you. So you do not need to deal with any file handling anymore. We will work from now on all the time inside Sapien, and we do not need to deal with more information or importing more information into the environment. So if everyone is good to go, I will go back to the theory to explain the first steps of the processing. No further questions, I guess. So let's go with the TIL series preprocessing. I don't want to go very into the details of everything, but just for you to have an idea of what we are doing, apart from pressing buttons and learning Sapien. This TIL series preprocessing is going to be, it will consist on 3 steps, in each of them we will solve a particular problem that we will address. We will start with an X-ray filter. Very, very easy, but we are, as we said, we are radiating our sample with electrons, and sometimes with these electrons hit the matter, it might generate an X-ray photon, an X-ray ray. And if one of these hits our detector, it might, let's say, blind the pixel or overdose the pixel. So, well, overdose the pixel. So this is one kind of artifact that we want to remove. Then we are going to make a dose correction. So here the correction might be a little bit trickier than for those of you who are familiar with SPA, because here we not only consider how much radiation our sample gets, but also in which direction. So if you think about it, our sample is thick, and if we move it and radiate it, some regions might get more radiation than others. And also, this is the other important thing about the dose, how my images, or in which images or in which order my images are acquired, will change the dose pattern, because those images that are acquired the last will have more accumulated dose than the ones that are acquired at the beginning. And this is why the dose pattern is something important. In the order in which you acquire the images, the more deteriorated the images get, and the last image will be more deteriorated than the first ones. And finally, resampling. This is a very easy steps. And basically here you can think it of 2 ways, whatever is easier for you. You can think that we are making our image smaller. So we have an image of a square of 144 pixels, and we are bringing it by 2, which basically means reducing the length of the sizes to the half. So you are reducing the total amount of pixels by 4. And there is basically 2 reasons to do so. First of all, save disk in space, save some space in disk. This is something that, if some of you have previous experience with tomography, have seen that it's important, because you get a lot of data, and when you reconstruct, things get very big and very heavy in disk. So this is something that might be interesting for you, and especially for some applications where maybe you do not need to go to full resolution. And this is the other way to think about it. Instead of reducing my sizes, increasing my pixel size. Maybe this is less intuitive, but in case this is easier for you. There is another reason to do so, and it's saving some computational time. And this is because most of the images relies on algorithms that make operations through the images, and the bigger the images, the heavier these operations are. So you can save some time. So if nobody has any theoretical question, we are going to go back to Sapien, and we are going to start working with our deal series. First of all, before going into that, I previously forgot. There is not only information holded inside Sapien, but there is also the binaries. There is also the actual images, and you can see those images inside the Sapien environment. In order to do so, we will go through this, but here will be holded all the output objects. So if I right-click on the output object, okay, this is not working for some reason. Okay, here, if you right-click in the object, you will see a bunch of viewers that you have available with. Some viewers are more related to information, like the data viewer or the Tomo data viewer, in which you can see information. For example, let's open the data viewer. Data viewer. Okay, here it is. Sorry. And I opened it twice because I'm very impatient. I'm sorry. So here, for example, you can see the data viewer. So you can see our 3D series and some information related about them. So, for example, I don't know how many images have them, or the sampling rate, or the voltage, the spherical aberration, all those things that have been read from the MDoc, the dose per frame, all those things that have been read from the MDoc are now held in Sapien, and you can access this data. And if you are curious, if you want to know it, you can go into these viewers and you can check for this information. But if you rather are interested more in your images, in seeing your binary images, then I would really recommend to use the IMOD viewer. So again, right-click on the output and press IMOD viewer, and this window will pop up. And this window shows the 3D series that we have imported. And I wouldn't click this place all at once. Basically, it will take a lot of time to load all the images. But we can look them one by one. So if you double-click in one of them, for example, the first one, Sapien will open this viewer. Since and this is something, as you see, it's taking some time. So this is one of the reasons I commented before why we used to bin our images, because things in tomography might get a little bit big. For example, here, think that you are opening images that are 5,000 by, or almost 6,000 to 4,000 pixels, and you're opening 41 of these images. So it might get a little bit slow. If you are very curious about, you can leave it to the second plane and let it open. Meanwhile, we are going to execute our first protocols, and then we can see the series. So close this window, please. And as I said, we are going to start with the X-ray filter, the X-ray eraser. So as previous, we have two options. We can go to the TIL series section, to the TIL series preprocessing section, and search for the X-ray eraser. Or if you have a lot of plugins installed, so you cannot find it, you can just here Control F, type X-rays, and it will appear. So this is a very easy protocol. We are going to leave all the parameters by default. In most of the Cypium protocols, you will have this advanced toggle, which shows to you. Okay. So let me a second, and we will touch on this later. So here you have this advanced option where some extra parameters that are more technical parameters, and if you are not familiar with the algorithm, might get difficult to interpret or to use. So I generally recommend the normal view. This is a personal feeling. And for this protocol, the only thing we have to input is our previous TIL series. So if you click here on this search button, you will see all the set of TIL series that you have inside Cypium. From now on, you only have one. So because there is only one protocol and we imported it. So we are going to select it. Okay, we select this protocol. We select this set. With this set selected, Cypium has all the information, or will underneath handle all the information from the set to execute the protocol without you need to specify anything else. So if everyone's fine, we click on execute, and Cypium will launch this protocol. While it's running, I will go back to the IMOD viewer just for you to see. This is a viewer that we are going to use a lot today, and it's the basic IMOD 3D mod program. It has a lot of applications. Here we are only using it as a viewer. Basically what you can do here, well, there is the page up and page down commands will move your image. And basically here you can go through the images in case someone is for some reason spoiled, you can detect it. Maybe you are just curious about how your acquisition went, on how the data looks. So it's a very convenient viewer to do so. It's very comfortable to use. And this, I'm going to advance some information, but these black dots here that you see, these are the gold bits. We are going to go later on what they are and what they are used for. But yes, these are our gold bits. So I'm going to close the viewer. I'm going to refresh the page. And Cypium it's running, the X-ray is running. Outputs are for some protocols generated, let's say on the fly, but some of protocols are not. So here, our first images have been already corrected. Our first set of TIL series. So our first TIL series inside the set has been corrected, and it is still executing. So if anyone has any question, this is a good moment. And if not, we will wait a little bit. Let's check the chat. Okay, I see you already got answer, Dimitri. Okay, if you are very impatient, as I am, you can click on refresh, and every time the Cyprian executes a step, it will let you know. Okay. Yeah, I see some of you are typing. I'm not going to open this output for two reasons, basically because as you see, it takes a while to open it, and second, because it's a step that unless you have a very sharp eye and you have how to say it, you are very experienced with this kind of data, it's very hard to see the difference. So I mean, feel free to open it if you want, but it will. I'm not saying it will disappoint you, but it's very hard to see the difference between the original image and the X-ray erased images. Okay, no further questions, I guess. Stuck in step 7, the refresh button is red. Yeah, maybe you are a little bit like me and you press it too much. There have been some improvements done about it, so Cyprian don't crash when you are, but don't crash, don't get stuck when you refresh a lot of the time. So that's a very for the impatient people as me. It's a very good feature. Okay, so can you start building the tree by just adding protocols, connecting the previous still running protocols? Okay, so this is something that has not been implemented yet. It's in the roadmap. This is what we call streaming or streamified protocols. We have the aim to do it, but still it's not. It's a we know it's a good spot. It's, as I said, in the roadmap, but still it is not possible. Hey, green on this. So, well, as I said, I'm not going to open the output because it will take long. But once we bin our images, I will promise you everything will go faster. And as I said, once we have finished our X-ray eraser, we are going to filter our images. Okay. Still at 8 out of 10. Okay, so I will wait a little bit longer. So okay, let's go back to the chat. Are frames within every single till motion correction already? So for this case, we are working with already. We are importing till series, not till series movies. So the frames are previously corrected in our data. Later on, if we have time, we will work with some with some movies for you to see the difference and the previous steps that you might need to take. You're welcome. Okay. I don't know if some of you are still. Is everyone finished? Just for launch the next step. Still on 7. Okay. Yeah, this might take a while. This is what I said. We usually bin our images. Hello, a quick question. If you have a long tomogram dataset, 25 tomogram, is it recommended to import all the tomograms at the same time or choose a small set of data with interesting tomograms? Okay, this is something that I would say, I mean, the easiest answer is it depends, but I will try to elaborate a little more. But it depends. So, for example, imagine that for some reason you need to do some checks, some first checks of your data. I don't know, you want to fast get a bunch of coordinates to see how things are going on, or you want to see your tomograms very soon. Then I would recommend to go first with a small set because it will speed up all the process. Because as I said, in tomography, things might get slow, might get slow and heavy because it's very intensive data. But if you are very sure of your data, or maybe you finish this first round, okay, you reconstructed 3 tomograms, you see how it looks, it looks fine to you, then you can go for the whole set. But imagine that you are super confident with your data and you feel, I don't know, you feel confident, you say, okay, or whatever you feel confident or not, you say, I want to go for full tomograms, I have resources and I have all that I need to, it won't take that long, or I can afford it. Then you can go for the whole data set. Generally speaking, the harder the problem, the more recommendable is to start with a small set. If you, for some, or the harder the problem, or the harder the step. So think, for example, that the problems start in the picking. Then you can go for reconstruct all your tomograms at once, and then take some subtomograms, make a subset inside sample, and work with them, and work with a small subset. It depends, I would say, on where your problem comes, or when the things get messy in the workflow. But as I said, there is a lot of it depends in tomography. Okay, so I don't know if anyone is still running. I see a lot of finished. Not yet, still on 7. Still on 7, okay.
Federico?
Yep.
Sorry, this is Maria Jose, and I've lost the connection to the UNC, so I have lost all the explanation. Could you do a summary just to know what you have been doing?
Okay, sure. So we are.
So I've lost the connection till from the selection of the TIL series, from that point.
In the X-ray eraser, you mean?
And when you have to select the TIL series of the day 1.
Okay. Okay, so you have your imported series finished? This first box, is it done?
Sorry, I haven't done anything because I've lost the connection. So I couldn't open the files.
Okay, I see. Then
Fede, if you don't mind, Maria Jose, we can go to a breakout room and I can explain you in detail while Fede can continue. Even go a little bit further just to allow you to go back and stay at the same point.
Okay, I'm in a private chat with Pablo.
Okay.
He's trying to fix the problem.
Okay. Okay. All the material on the videos and all the guidelines will be published. I think they are also available at this moment, just in case that someone get due to any reason very lost. due to, for example, technical problems, just to have the chance to reach the point of the rest of the people are in.
Okay.
Okay, if it's everything fine, thank you, Jorge, for the support. So, well, I don't know. Okay, some people are still processing. As I said, well, let's take some time then to go for the Scipion fields. As I said, here you have the summary, the methods, and the output log. In the summary, you have a little bit of sum up of what has been done, the input, which is our imported till series, the output, which is an X-ray corrected or X-ray erased till series, which, as you can see, they do not change in size or number. It's just has been processed. In the summary, you have basically some information related. Some protocols are more verbose, some of them do not need it, but basically you have some information about how they are the processing that has been carried out. In the method section, you have a more of a detail of the things you have been done, the program, for example, that has been used in IMOD, some references of the underlying algorithms if you are curious about, or you need, I don't know, to put it on a paper, or you will have the information. And finally, as I said, an output log. This is a little bit less intuitive maybe, but it will give you information about how things are running in the background, what the operations that you have done, the call to the programs, for example, the output of the raw output of these programs, these kind of things. Is anyone have we all finished? Is anyone still processing? No, yes. Okay. Okay, in the meanwhile, I will, because I don't want you to extend the day that much. I'm going to start explaining the next step we are going to perform, which is the dose filter. So I will repeat it again when all of you finish, but just for you to know. So as I said, you can search for it, or you can select it in the left panel. And again, here you will have to select the T series that you want to input this protocol. In this case, will be the output of the previous one, the X-ray eraser. As I said, we have a bunch of advanced options. We are going to ignore them to keep it simple. And I will take some time to explain this. So this is one of the advantages of the MDoc, as I said. It would be very complicated to input the dose manually, because it's not only how much you have radiated each image, but also the order, as we said, in which you have radiated them. And this is one of the good things, or one of the reasons that I hardly recommend to use the MDoc files as an input source of information, because since, well, here you have two options: Scipion import, which is basically use the dose from the import, and I've used an MDoc, so I know I have some information here. If you hadn't, for example, Scipion will give you a warning, will say you, hey, you did not input an MDoc, you did not input any of those information. So, but in case you have, sorry, in case you have inputted those information at the beginning, the Scipion will hold it and will use it. The other option from this protocol is to use a fixed dose for every image. Sapien will still use the order, but you will correct all the images with the same dose. And this is, if you can avoid it, this is not recommendable, since it's better to know. You can introduce some miscorrections, since not all the images have to be radiated with the same dose. Okay, so I don't know if are we all finished. A small question: does the X-ray eraser estimate the damaging effect of radiation applied on the series? It's a good question. Actually, not that much, because it depends on the interaction between. It depends on the interaction between the electrons and the sample. It is true that the more radiation you get on your image, more probably is to generate an X-ray. But it's not a measure of that. It's actually the protocol. What the protocol does is just to look for those pixels that have been blighted, that have been overdosed. The protocol just look for those pixels inside a region we have an outlier value, not made like a study of how this interaction happened or not. About the function of this protocol, as I said, this does not. It's not easy to see at first sight, but these peaks generate some artifacts in the reconstruction. So if you have a very wide pixel, in all the projection in that direction, the algorithm of reconstruction will consider a very high value, and this might introduce some artifacts in the final reconstruction. Okay, are we all good to go? Is there anyone still processing?
It just doesn't proceed from 8 of 10.
It does not proceed to 8 of 10.
Since I wrote I'm at 8 of 10, there's nothing going on, kind of.
Yeah, it's a heavy stuff.
Have you hit refresh?
Still processing.
Several times, yeah.
Okay. Because it's not refreshing continuously, so it delays the refresh. I don't know, maybe it's taking some time.
And sometimes it works immediately after I'm pushing refresh, and sometimes it takes some time.
Okay, so if you don't mind, since we are approaching to the break, I'm going to launch the next protocol, and once it finishes, please let us know, and we will catch up. Okay. And I hope it finishes soon. It shouldn't be taking that long. So, well, as I said, the next step is the dose filter.
Fede.
Yep.
Evgeny has a question in the chat.
Okay. Let me launch the protocol, and I will answer the question, please. So, well, as I introduced, for those of you who has finished, we have to select the TIL series that has been output before from the X-ray filter. So if you haven't finished this protocol here, you only would see this one. But for those of you who has finished, this will appear. So we just have to select it. Leave the input dose source as Sapien import, because as I said, we have imported from the MDocs. And it's the most precise source of those that we have, and just click on execute. And now I go to the questions in the chat. Okay. Regarding the fixed doses and input, does it imply that the acquisition scheme is continuous? No. will use the order information from the MDoc, or from the or from any input that you have set. So Scipion will necessarily need to know the order of acquisition. If not, it will assume continuous if you don't say anything, but you should. And actually, it's a fixed field. So if you don't know, you can set it to continuous or to whatever, but you have to input some order information. And Scipion will use that order. What it will do is to use a fixed dose for each image, but in that order. So you cannot. It has not implications in the order. Only has implications on. Sorry, only has implications on the dose used for this. So this protocol is way faster than the previous one.
Sorry, Fede, is an option to skip the X-ray eraser and just
yeah. Okay, let's put it that way. For those of you, if you are taking too long, here in the dose filter, instead of selecting the X-ray that won't appear, well, it might appear, but with less than 3 items, click the input. The import is series. We can see even the difference between the two executions, and with a little bit of luck, we can see some artifacts in the non-X-ray erased field. So, is anyone still running? Well, I already said so. Let's take a little bit of time. I will. So what is the dose filter now doing? It is estimating the dose, right? It's a weighting dose filter. It's similar. Actually, IMOD uses I don't remember now the paper, but it used a classical dose filter approach. It just applies it to every image, considering the accumulated dose. But it's not. Well, it's estimating the effect. It's a dose weighting filter. So is anyone still running the dose filter? Yes. Okay. I will wait a little bit. Okay, that's the paper. Thank you very much, Carlos. It's actually it's that one. It's one from Gregory from Grant. Okay, finish with the build series as import file. Okay. Okay. I'm sorry about that. It shouldn't have taken that long, actually. So if everyone's finished, we are going to move to the last step in the pre-processing, and we will have a break. Is anyone still running the dose filter? Okay. Okay, then in that case, we are going to move to the last pre-processing step, which is the binning step. For this, we are going to use a normalization protocol, the IMOD one. So if you type IMOD normalization series normalization, because we have a version for tomograms and a version for T series, so it's IMOD T series normalization protocol. You just double click on them. As input T series, we use the one out for the dose filter. The binning factor we are going to use is 4. We are going to make the image actually 16 times less weighted. weight, and only we are going to reduce its size by 4. And the rest of these are parameters according to the data type used or the densities. It's a very complete protocol, but we are going to leave everything as default because we are only interested in binning the images. So we just set 4 here for binning 4 and click on execute. The protocol is this one. Where is IMOD located in the work tree? We are okay. But a second, please. We are not changing the signet, the byte options. Okay, we are leaving these 2 as default and this one as no. It won't change a lot, but I would rather leave disrespect the input data type. It won't change it, and the same with the density. So leave these 2 as default and set the scaling values or no. And the IMOD is located in the work tree. It's not a location for IMOD. IMOD have a bunch of protocols, and these protocols can go in and out in the tree protocol or in the pipeline of tomography.
I think Dimitri is asking that specific protocol of normalization.
Oh, this protocol of normalization. Okay. Sorry, Dimitri. Where does it go? Well, it depends again. It depends on the pipeline. The sooner you use it, the sooner you bin your images, the sooner you will have the benefits of reducing the size.
Sorry, Fede, I think it's in the tree, right? Or maybe Dimitri, you say
in the tree.
In the left tree. Is it
okay. Sorry.
Yes, I was basically looking for the location of this protocol within the tree. Yeah, and what I see is that yes, here indeed, and it's above previously executed, because yeah, like normally in Cyprian we have everything that has to be done like one after the other. That's my question, why this one is a bit above the one that we already did, like dose filter or X-ray eraser.
Okay, I see.
I recommend to, because locating on the tree is nice because it gives you an idea of what is available. But if you know the name, I think probably is more straightforward to go to the project menu. Maybe you can do it, Fede.
Right. Yes. What I mean is a sequence.
Yeah, and then you will be presented with the searching window, and by typing you can that window search for a protocol, and that will probably locate any.
Yeah, at the end we have that much protocols that might be easier to look for it rather than how to say so, rather than looking for in the tree, just because it can get a little bit messy. So the TCS normalizations can be used on the very first step to bin raw data too. Yes, for sure. So okay, binning, it's well, I will answer this and we will go to the break. Binning is it's not an irrelevant step, precisely because depending on when you execute it, you will bias the rest of the workflow in the front. Okay, so there are some information that you might get. For example, we will align some T series. When we align the T series, we can have a binary align, or we can have the information of the alignment, and we can use this information in another series. That, imagine, for example, my binned and my not binned series. I could align one and go to the other, but for some operations it's not. Those bit operations where you affect the binary directly, and for example a dose filter, once you bin and you dose filter, you are dose filtering the binned images, and in that case there is no way to go back. So the good thing of binning is that you are going to go faster, but it's not always what you want to do if you want, for example, imagine, I don't know, imagine that you want a full reconstructed tomogram. Imagine you want your original size tomogram. Then in that case, you cannot pinch your images. And you have to do the process of before the tomogram reconstruction with the original size. So it's a trade-off at the end. And that's one of the things that I say about tomography, that the workflow is more open, that it's not absolutely answers to everything. They depends. Answer comes very, very at the beginning in every processing step. So if there is no question, we are going to take a 10 minutes break, and I will see you at 11:30. Let me have a second. I will drink some water, and I will back to you if anyone has to catch up or needs some help. Hello, Tamara. Thank you for answering. Okay. Okay, then we are going back. So I hope everyone has this series normalized. As we were saying before, these binning processes, what is doing is reducing the size of the tomogram, or you can think it as increasing the pixel size. So it's exactly what we can see in the output. Here you see how our images are reduced in dimensions or are increased in pixel size by a factor of 4. So things are working on. CPN is handling properly the output, but the output files and correctly detecting the dimensions and the pixel size. So we finished the preprocessing. Okay. X-normalization, X-ray ratio has not finished yet. Okay, leave it there. We will work with a normalized series. It's okay. So now we finish our preprocessing. I'm going to go back to theory because now it's time for the alignment. Alignment is a very tricky step in tomography. They are algorithms that solve a kind of complex problem if you think of this amount of data they have to handle, and also the quality of this data. Tomography, we have a very low signal to noise ratio, so it's a problem that sometimes can get a little bit tricky to solve. That's one of the first reasons why we are working with gold bits. Gold bits are this black. Is there any question? Okay, so gold bits are these black dots that you are seeing. They are basically bits made out of gold. And the reason why they are there is because they are, as you can see, they look very, very sharp and very dark, and they are very easy to locate in the image and through the images. So the technique, what it does is to add these gold bits to the sample and then take the images. So you have reference positions inside your tomogram that you know where they are in the whole in the whole set of images. So I have the same pattern of gold bits taken at different perspectives through the tomography process, to the D series acquisition. Okay. As I was saying, this is a complex step. Actually, it's breakdown in 3 sub-steps, the alignment process. Okay. But the first question is, why do we need to align? It's basically because there is no way to reconstruct a tomogram with misaligned images. But where does this misalignment come from? So basically, it comes from, first of all, the movement of the sample, which basically the holder, when it rotates, it shifts a little bit, so an image doesn't fit perfectly to the next one. And the second reason we will see it in a minute. But let's start with the pre-alignment. So the pre-alignment, basically what it does is to correct the movement, the relative movement between 2 images of the set. Actually, between all the images of the series, and they generate a pattern of shifts that make the transition smooth from the first image to the last image of the series. In these steps, only the shifts are corrected. This is important. We will see later on why this is important, but it's important you get with the idea that the images are only moved up and right, up and down, left and right. Okay. So we are going to go back to Sapien, and we are going to perform our X-core pre-alignment. So this is held in the T series section in the alignment section. Here you can see it, or you can just, as I said, look for it with the Control F with the search protocol pop-up, and at the end you will have this protocol. Okay. So sorry. We follow the previous logic that we were doing. We are going to input to this protocol the output of the last one, and we will keep constructing the tree inside Sapien. Okay. So as an input, I'm going to select the normalization output, as you have 3D series with this smaller dimension. So this is my set. This is the correct set. So I will select it. For this case, we are not going to use cumulative correlation. It's basically another different algorithm that solves the same problem of correcting the shifts between images. And this is and the next one, we are going to generate the interpolated series. And this is something I need to spend some time, because it's very important for you to understand it in order to understand how it's all the logic of alignment implemented inside Sapien. But first of all, in order to save some time, we are going to execute it. So wait, please. Sorry. Don't click on execute. Let's change the binning of the interpolated T-series to 2, just to make the output a little bit smaller. And now I will explain what is the output, but please, now, yes, click on execute. So why is this logic of interpolating about? As you can see, in the alignment process, basically what we are doing is to move images, one respect to the others or respect to a common reference, but we are moving them. And this movement can be held, all this information, all this movement information can be held in form of matrices. It doesn't matter the detail, but what you have to be aware of is that all this information can be held as text, and text is super cheap. It's super cheap in disk. So that's one of the reasons what we do not want to interpolate in every step we are doing, because we want to save some space in disk. Because as I said, the interpolation process, it's iterative. We have
Federico, sorry. How have you run the pre-alignment? Could you do it again, please?
Sure. So you search for it. You search X-core, sorry, and it will pop up. It will appear this protocol, IMOD X-core pre-alignment. You have to input the T series. You have to input is the output from the T series normalization protocol. Okay. You select it, and in the generate interpolated T series, you select it to yes, and set the binning to 2. Is okay?
I need it.
Okay, it's okay. Take your time.
Thank you.
Oh, you're welcome. So as I was saying, first of all, we are saving a lot of space in disk, saving this interpolation step. But there is a second reason to do so, and it's to save interpolating images.
Sorry, Federico. Sure. Where can I find the search, Tom?
The search button is this, I don't know how to say lupa in English.
Okay, lupa. Okay,
no, I think,
lupa is fine for me.
Maria Jose, you see the project menu. You see the project menu on the top left.
Ah, okay. You mean the sorry.
Can you click there?
Where?
On the top left, Fede, maybe you can click on the project.
Okay, it's the protocol is located here in tilt series alignment section X-core pre-alignment.
Okay. Okay. What? Wait a little.
Sure.
X-core.
If not, you can look for protocols. If you click on project and then a project up there, and then it says something like search or something. Search.
Okay. Okay. Thank you. I'll try to do it. Fine. Sorry.
That's okay. It's okay. Okay, then. Sorry. Didn't want to do that. Okay, so interpolating, saving interpolations. So there is this first reason, which is that we can hold all the information in a TXT file, and that's very, very cheap in space. And there is a second reason, because we want to save interpolations. That is that you do not want to interpolate a lot your images. You don't want to interpolate and then reinterpolate and then reinterpolate. And alignment, as I said, is iterative. So you want to save as much interpolations as you want. And why do you want to do so? Okay, saving interpolations is important basically because you have to think that every time that you're interpolating, you are recalculating the value of some pixels. And you can lose some detail there, especially with rotations. So that's why you want to interpolate the less number of times. But you want to see your results. You want to see if the alignment process has been done correctly. And that's why we need to interpolate, because we want to see if the pre-alignment has overcome properly. So this is the one that we want to use for visualization purposes, for judging how good is our interpolation, how good is our alignment. So that's why we are generating. And why binning 2? Basically to save some space disk, and because you do not need very high resolution, very detailed image to see if your alignment have gone wrong. If your alignment have gone wrong at low binning, at high sampling rate, you can judge it. So that's why we are setting it 2. But you could just leave it to 1 if you have massive massive space disk. Once the pre-alignment it's concluded, we can judge the results. But well, let's do it now. So again, if you right-click, and this is very important, if you want to see your results, you want to see the interpolated one. And I want to insist on this, because if you visualize this one, the output set of this series, you won't see any alignment, because the alignment has not been performed, has not been interpolated. It's saved as test, as I said. So that's why you want to visualize this one. So right-click on the interpolated set, IMOD viewer, and double-click again. This should open faster because our images are very small. This is another good thing of binning. And this depends on how good your connection is. If you right-click on the image will move. But if your connection is not good enough and you see jumps in the image, you can move slowly by page up, page down. And here you can see how now the transition between the images is very smooth. The one gold read and the next one is very close, and the next one is very close, and the next one is very close. And here is the first step of alignment. And I mean, I really hope you have a good connection, because it's very pleasing to see things moving. But if you don't, the page up, page down button will make it. Now, let me continue a little bit, and I will go to the questions, please. So now we have pre-aligned our images. Our transition between images is very smooth, but the thing is not problem. The problem is not solved yet. And why is that? It is because when you want to reconstruct, you are not only want smooth transitions between your images, but also that all your images are rotating with a reference, let's say. So all your images now are aligned, so they are moving smoothly, but they are, and they have all the same location for the tilt axis, the rotation axis. All of them are now rotating respect to the same axis. But this axis is rotated itself. The images are not rotating vertically, let's say, they are rotating, they are moving, but the axis is rotated, okay? It's a little bit spinned. So that's why we are going now through the fiducial model generation, because we want the images rotate vertically. We want that tilt axis rotation. The tilt axis location is vertical with respect to the image. And why is that? There are some reasons, but the most spread or the most common one is just because of how the reconstruction algorithms are generated. Because this rotation of the tilt axis will allow you to apply different strategies for the reconstruction that we will see later that are very much faster and very less intense in memory usage. And how this fiducial model works? Well, basically, what you need to do is to assign to know each goal bit, or at least some of the goal bits in one image, which one are in the next one. Okay, so for example, I don't know if you can see it, I hope you can. But if you see here, some pixels are colored, have like a yellow circle, and if you don't see it, you will have to believe me, sorry. And this means that IMOD has detected this goal bit and has detected that the next one, in the next image, this goal bit corresponds to this one. And if you do so and if you generate these chains of goal bits through the series, with enough of them, you can understand the underlying movement of the tilt series, and you can correct the position of the tilt axis. Okay. So let's go back to Site and let's generate our fiducial models here. So again, we can search for it in the left panel under tilt series alignment, generate fiducial model. Or we can Control F and look for generate fiducial, for example, here. And here you have it, generate fiducial model. Now, there is two things that are important to solve here. The first one, your input tilt series, which is, well, as always, you have the advanced option, but we are again going to ignore it. And you have to select your input tilt series. It's very important that you select the non-interpolated this one, okay? The 5.3 Armstrongs per pixel resolution, not this one, because then things will get smaller and smaller, and you end up seeing almost nothing. We generated just this one just for purposes of seeing how the pre-alignment was performed, but we do not want to keep processing that image, okay? So we select this one, and the second one, and this step might be a little bit trickier, is knowing the size of your goal bits. Now you will have to believe me and know this is 13 nanometers of radius, okay? I will go now in the details, but please set 13 here. Select your input as the pre-alignment output set of the series, not the interpolated one, the output set of the series, and click on execute. And now, why is well, first of all, I know there is a question about binning. Does binning in normalization job sum with the binning in the X-core pre-alignment? The answer is yes. Okay, the answer is yes, because what you are doing is binning your input images. So binning the images is also iterative. You accumulate the binnings. So you have to be careful with that. If you keep binning, you end up with basically nonsense images because you won't be able to see nothing. And and now about the size of the gold bits. I'm going to, we have generated a new output inside Cypium, and if you see here, we input some set of till series, but the output is not longer a set of till series, it's a set of landmark models. Landmark models, fiducial models are the same. It's our abstraction in Cypium for holding this information. And we are going now to visualize how this went, how this was processed. So again, right click, open with IMOD viewer, and let's open the first one, for example. Let's open the first one, for example. Okay. And here you can see what I was saying. Gold bits are, okay, see, I'm very impatient and I open it twice. IMOD is going to detect our gold bits, and he has, for example, he looks at this gold bit. He has marked it through the whole series. So now he knows that this gold bit is the same gold bit in all the images, and he is able to align posteriorly the images. Okay. About the okay, I'm going to stop it. About the size of the gold bit. This is something that you might know from acquisition. For example, in Empire, some of the entries report the size of the bits, but in case they don't, you can measure it. You can any visualization tool, or if you I don't know, maybe you are you have used ImageJ or any other tool for visualization, and you can measure the size of the gold bit. But be aware that you will be measuring it in pixels. Okay, so you will have to multiply it by the pixel size. I think there was a question about this before, about the size of the gold bits. The size of the gold bits, this one, Fernando Lamos. The size of the gold bits depends on the binning, or you input the real size of the gold bits. This question, it's very important. It's very interesting. It doesn't matter in the sense of the measure here is in nanometers. It's not in pixels. It's in nanometers. Okay, and that's why it's very important to know the real size, and it's very important to multiply by the pixel size, because the higher the sampling rate, the bigger in pixels, but the size in nanometers, it's the same. So this number won't vary if you measure at binning 1 or at binning 8 in nanometers. Although in pixels it changes, in nanometers it won't. Okay. So just realized my data says, okay, that looks like you haven't used the output. Okay, Pablo will take charge of that. Okay. Okay, thank you, Pablo. Okay, so if everyone has finished, we are going to end up with the alignment step. Is everyone finished? Is anyone still processing this step?
So I have a question.
Okay.
How many gold beats does IMOD has to track correctly to achieve a good alignment?
Okay, it's a very good question. Again, it depends. But in my experience processing, I've seen set of images with IMOD detecting 3 gold bits and aligning well, aligning very fine. And I've seen images with a lot more gold bits detected and doing it very bad. So I do not have a question about it. The intuition says that the more gold bits you have properly located, the best your results should be, because you should be able to refine better the alignment. But at the end, that's not always the case. At least in my experience as processing myself. I'm not a professional data processor, okay? But the things I've tried, I've seen both things. Also, I haven't mentioned it, but here in the advanced parameters, there is a number of fiducials. IMOD also does his best here. You hear we might say 15, we might say 5, we might say IMOD does his best. If you say 5, it will search for 5. But if you say 25 and there is no 25, it will take it will do his best. It's a best effort strategy in that sense, okay? But I do not have a number. I'm sorry, because also depends on how hard your images are to align. So yeah, I guess it depends again.
Federico, I also have one more question. So on your presentation, we've seen that also the beads were colored differently. So there was a green label. It's one thing. Another question is, when we so the IMOD marks them as green, but can you do it like manually? If IMOD fails, can you set it up like?
Yeah. Both good questions, both. About the color, okay, this is something off the record, but okay, this is nonsense. Okay, this is just the images I took for the presentations because they were beautifully located and I like it. But this color, it depends on if the images are in front or behind the sample, but in cryo electron tomography, this distinction doesn't make that much sense because sometimes I don't remember which technique it is, but in some techniques you just cut lamellas and put gold beads so you can make this distinction if they are in front or in behind, for example, with resins. But here it doesn't make that much sense. So this is just, it shouldn't be pink or purple. I'm color blinded, so I don't know the color of this. But and the second question was
the manual possibility.
The manual. So yeah, I don't know if we are going to have time, but there is a manually approach to marking fiducials. It's held inside the eTomo interface. And we have the interface of eTomo hold it inside Cybian. So it could be the case that you have some data that, for example, you have 100 T-series and maybe 20 of them are impossible to align. And sometimes this problem not comes from the pre-alignment, but for the alignment calculation, but for the detection of the gold beads. And in those cases, you want to go manually, or there's maybe the only solution. I mean, if IMOD doesn't work and any other software doesn't work, maybe the only option you have is to mark your fiducials manually inside the eTomo. But we don't have this tool separated inside Cybian, but it's held inside eTomo, so you can use it. I insist, if we have time, I really hope you can see some of the eTomo tools inside Cybian. Okay, so if it's everyone correct, if it's everyone finished, I'm going to sorry. Sorry. If we all have finished this step, I'm going to go through the next one and then answer more questions because I don't want to steal time for lunch. So what happens, as I said, okay? So I have detected my gold beads, and now I know where they are. Since I know where they are, I can rotate my images, whatever each image needs to be rotated, in order to have all them rotating through the same axis and locating this axis vertically, okay? And this step is done in the final fiducial alignment. So we are going to go back to Cybian, and we are going to select, it's under T-series alignment, but you can search it in fiducial. Here is fiducial alignment. And the input, and this is, if you think about it, this is a Python, but it's very, very logical. The input is the previous model of gold beads generated. Okay, so you should only have one, and it's the one generated in the generate fiducial model previous step. So we select them. As I said, find onto surface, no, because it doesn't make sense in this kind of data. In some other may does, but here it doesn't. And as in the pre-alignment, we are going to generate interpolated T series in order to see how the alignment is performed. And I'm going to bin it again by 2 just for saving some space in disk. Okay. So input generate the model, find onto surface, set it to no, and generate an interpolated T series at bin2. Okay. So let's execute it. And let me go to the chat if there's any other question. How to apply gold bits on the lamella after milling? I'm sorry, that's out of my knowledge. I have no experience in sample preparation. If you mean in the processing, just click on detect onto surface in the generate fiducial model and also in the fiducial. So this has gone fast. Now again, we can see the outputs. Here we have even more outputs, and I want to explain it a little bit, and then we just need to reconstruct the T series. So as before, we have our output T series and our output interpolated T series, which is again binned. We can use it. We are going to use it just for looking at how the alignment went. We have a new set of landmark models. This might look not very intuitive, but it makes sense. Think that when you select your landmarks, you might miss some images, and in that images, you might not see. You don't detect the landmark. For example, I have a change that goes from image 2 to image 12, and I have another that goes from image 8 to image 25. They are missing. So once I'm aligning the image and everything is properly aligned, I know where these are now located because I aligned it all according to the same axis, and they are all rotating, let's say, harmonically. So now I know these points that I were missing. Now I have it, and that's the output we have here. And finally, this is more an IMOD feature that also gives you the location of these gold bits in the 3D space, because if you know which gold bit is in, where one gold bit it's in every image. Now I can calculate where is its position in space. But besides these two, we are going to focus in our interpolated series. So again, right-click on the interpolated one, open with the IMOD viewer, and if everything went fine, that I hope so, now we should have our properly interpolated series. So now things move smoothly. I hope you can see it properly right-clicking. If not, move it with page up, page down. But as you can see, image is still moving smoothly, but also it's rotating vertically. So now everything rotates vertically fine. And now we can input this to the reconstruction algorithm. And this is it. We have our images aligned. And that's very, very great. And with our images aligned, now we are ready to reconstruct. This is one of the most tricky steps in the first moves of the pipeline in tomography. Alignment, it's a process that might get tricky depending on your data. So it's very good that if you are able to do it automatically, you can save really a lot of time in processing, a lot of time. So if everyone have reached this point, I'm going to go through the final step, which is reconstruction methods. I am not going to spend too much time on this because Professor Vilas, my colleague, is going to spend some time on this and explain it in detail. But we have a lot of algorithms to reconstruct with different approaches and from different plugins. And at the end, this is kind of an inverse problem where you have projective information in 2D, which are your images, and you want to go from a set of 2Ds to a 3D. So maybe things get trickier because maybe you don't have, as I said, the missing wedge, the angular sampling, but at the end you are reprojecting somehow. You are taking information from 2D and combining them into a 3D volume, which is your tomogram. There are a lot of approaches to do so. We are going to use two basically, which are weighted back projection and SIRT. Weighted back project or SIRT is simultaneous iterative reconstruction technique. We are going to use two plugins for this. We are keeping on IMOD and we are introducing a new plugin called JJSoft. IMOD has its tomogram reconstruction and JJSoft, which will be recalled in some weeks to Tomo 3D. Both offers weighted back and SIRT, weighted back projection and simultaneous iterative reconstruction. And IMOD just offers kind of a SIRT-like filter, which is a way to reconstructing in weighted back algorithm, but applying a filter to look it like a iterative reconstruction. So if there is no questions, I'm going to go back to my Scipion framework, and we are going to start. For example, let's start with IMOD. So we abandon the T series section and we start with the tomogram section. In the tomogram section, you have many tools, but one of them is tomogram reconstruction. And here you have IMOD tomogram reconstruction protocol. You can also search for it. There's a lot of plugins that performs this step. We are going to keep with these two. So you select it from here. And reconstruction is usually very straightforward. You just need to input your T series, that in our case will be the output of the fiducial alignment. Again, please be aware to select the non-interpolated one, the 5.32 Armstrong resolution, because things then, if you know, things will get very small. And the thickness, we are going to set 300. This also depends on where is your information located, how big you want to go. If you very big reconstruction, very thick reconstructions will hold more space in disk, will take some more time. But at the end, you want to see what you have in your sample, so you cannot miss that information. We are not going to reposition it. We are not going to shift the tomogram. But it might be something that that if you see that your sample is not well centered, you might need to do. With 300 here and the fiducial output T series, we just click on execute. This algorithms runs both in CPU and GPU, so it's if you run it in GPU, it's quite fast. And secondly, we are going to use JJSoft, or as I said, it will be recalled to Tomo 3D. It's holded here, or again, you can search for it, clicking Control F and searching for Tomo 3D, Tomo 3D, 3D Spanglish. Here you have the Reconstruct tomogram. And very similar to what IMOD needs as input. Again, our fiducial non-interpolated one, the 3.32 Armstrong, the same one we have inputted in the other protocol. For the purpose of comparison, here we are going to select SIRT just to see the difference between both of them. Leave the number of iterations on 30, and we want to select the the shape manually. Again, let's say for them to be the same.
Federico?
Yeah, sorry.
Hi, excuse me. You have run the tomogram reconstruction and it's running. And what are you doing now?
This is the, okay, sorry, maybe I went a little bit fast. This is the JJ soft tomogram reconstruction. So if you Control F, you can search for it here, or it's located in the left menu under tomograms section, the tomogram reconstruction subsection, the JJ soft Tomo 3D. Did you see it?
Yes.
Okay.
Yes, I see it.
Okay, so double click on them. And now, sorry, that's okay. Select as input till series the non-interpolated one, the one which the fiducial alignment output set of till series.
One moment, please.
Sure.
Okay.
Okay, so select this one. Now the reconstruction method sheared, which is slower.
Okay.
And now we are going to set the manual tomogram shape. So select yes.
Okay.
And here in thickness, set it to 300.
Okay. And we are doing this while the tomo reconstruction is running?
This is another another approach for tomogram reconstruction. We are going to reconstruct two times the T series, and
Okay.
we are going to see the difference. So please click on execute, all of you.
Okay.
And this should be running. In the meanwhile, we can see the output of the other protocol. So here we have a new output. Now we abandon the T series board and we go to 3D. We have tomograms now. Tomograms, instead of number of slices, or instead of number of tilt images, has number of slices, a thickness. Sorry, I missed the parameters for the shear. Okay, maybe I'm going a little bit fast. I'm sorry. These are the parameters. So set sheared slow. Number of iterations, leave it as default with 30. And please set the manual tomogram shape to yes. And thickness to 300.
Okay.
Okay. Okay, if everyone has now both protocols running or finished, you're welcome. Okay, so as I was saying, now we have tomograms. So we are going to have a look at our tomograms. To do so, I recommend the IMOD viewer again. And we are going, for example, to open the first one. And now, instead of having information, projective information from different points of view, what we are going to have is a 3D information. So what we are going to see if we right-click is the image or the view moving deeper and in and out of the slices of the tomogram. Here we can see our gold bits, for example. They look very round and black and beautifully. And here we can see our viruses. So we are doing a good job. We have our viruses. As again, if you are used to maybe some other techniques, you don't see that much detail here. But as I said, in electron tomography, we have to fight with a very low signal to noise ratio. So things kind of get complicated. But here they are. And now a trick that I really like to use, if you have IMOD 3D mod open, and you click Control X, the X-ray or X cross correlation, X whatever. you will open this one, and here what you can see is not only the slices, but the slices looking in the 3 directions. That way, that left, right, up and down, and front and back, okay? And there is very useful tool, for example, for detecting misalignment, which is basically what my thesis goes on. And for example, if I click on a gold bit, you see, for example, this artifact. This is the missing wedge. This is what we were talking at the beginning of the talk. These kind of things that appear spreading, these are the missing wedge. And this is well aligned, but if it weren't, you would see artifacts moving around. Sometimes have the shapes of bananas, sometimes just go super blurry. But it's a very, I mean, it's a very useful view if you want to see a little bit more in detail what you have in your tomogram. For looking at the specimen, is not that good. So if, for example, you don't recognize your virus. So, and if I don't know if okay, this is JJSoft. This is still running. As we said, CIRT is a little bit slower, but you will see. As I said, Professor Villas will explain it later. But for you to have an intuitive view, weighted back projection, which is what we have done with IMOD, it's faster. But the level of contrast that you might get with CIRT can get a little bit better, and that's why you might see things a little bit more in detail. So, Control X, yes. Thank you, Control X. So, I don't know if I missed any question in the chat. CIRT will give you more contrast than so that's Villas, okay. So do I understand correctly that we are now testing several tools for tomo reconstruction? Yes. I mean, we don't have time, okay, but there are more tools that we could check. For example, a CIRT filter that could be also interesting to see. This is something, if we have infinite time, we could be playing around a lot of time, but we don't have it. So none of my current protocols are finished. I'm sorry. If you have at least, if it's not finished, but you have at least one output here, you can visualize it. Okay. So instead, you want to play around that. It hasn't finished yet, but you want to see it. If you at least have one, you should be able to see it. I don't know if any of you have further questions. Yeah, reconstruction, it's especially, I mean, also think that here we are working with binning 4, which times your tomogram is going to be 4 cubed times smaller, which is actually a lot. 16 by 4, which is 64 times smaller. That's one of the drawbacks. And not only think on computational time, think also on disk space. So 64 times is a lot. Reconstruction tomogram at binning 1, which might be necessary in some applications. I'm not saying it's not, but here you have, there you are computation or calculating a lot of information, saving a lot of information. So if you put things in context, it might get big, and things might get out of control when you are working in parallel with 100 series, for example, and you reconstruct 100 tomograms. Things you can get having terabytes and terabytes of information. Oh, look, it finished. So I don't know if it finished for you, but we are going to visualize it while it finished for you. Again, I will open the IMOD viewer, and we are going to open the tomogram. And as you can see, things now have much more contrast. You remember how your viruses look like in the previous reconstruction, and look at this. You could even see the spikes. So it's a difference. The drawback is slower, but again, you always need to make a trade-off of things. Maybe you want to, I don't know. Maybe you want to pick at with a weighted back, but then extract your subtomos from a sheared. So things got. You might even need, or you might even be interested in both, in using both methods in the same workflow. And again, this works the same. It control right click button, you see it, and if you set Control X, sorry, you can see this new window, and again, the missing wedge is there. So this is something. This is something that might that doesn't appear doesn't disappear changing the method of reconstruction. You have missing information, and you have to deal with it. Okay, I don't know if it has finished for you. Let's check the chat. Is thickness relative to size? Yeah, it is. Yes, it is. It will also depend on the thickness of your sample. But samples cannot get very thick, right? Because then you won't see anything. But for me, the T series 48. Okay, appears some strange line. Why? Did you run the X-ray eraser? Because if not, might be that. I don't. It's a pity I cannot see it, but if, for example, that's what I was talking before. If you have a very bright pixel and you have it through the series, I mean, you have projective information, right? It might get an artifact in the final reconstruction. So that's one of the reasons we want to remove them. Also, because it doesn't matter how we combine information with the rest of the views in that projection, everything will be blacked out. Is there any qualitative matter these two approaches can be verified? Just a very good question. At the end, what you are verifying, it's if you're, I mean, I don't know exactly what you want to mean with verify, but if you mean that the alignment and reconstruction process, apart from visual inspection in Scipion, we do not have any tool yet. This is my thesis project, and we do not have any tools yet to detect misalignment. But it's basically what you could detect, not that much. I don't know if you mean. I don't know if you mean any other kind of inspection, but if you are talking about misalignment, there is no tool yet to do that automatically. If you have a trained eye, there is some artifacts you can see consistently. For example, there are some kind of noise, some kinds of misalignment that always end in the same type of artifact. So that's another thing. That what was the tomogram saved with? Yes, 300. Thank you, Pablo. Just to have an idea of how this will run, what are the specs of the machine we are running on? I don't know. I know someone might know, but I don't know. I know we have a GPU.
I will ask and paste in the chat.
Okay, thank you. Thank you very much, Pablo. Okay. I don't know, I'm sorry, but another point is for example, if you're worried about time, it's a qualitative difference between the algorithms, between sheared and weighted back, but it will get more significant when you go to bigger sizes. So that's another thing you might be aware of. But here in the lab, we have some people processing, and they have spent time reconstruction. So it might, they work with very big loads of data, but it's something that might get time. The good thing is these programs are parallelized. So if you have a very powerful computer or several GPUs, I don't know if with several GPUs. I know, but if they are parallelized, in theory, you should be able to max out the usage of your infrastructure, of your devices. So I don't know if we all finished. I think a very useful system is the mobile control X. Some of the M frames. Yeah, it's very useful. It's very useful. And 3D mod is the IMOD viewer program. It's a very powerful tool. I'm not an expert in IMOD per se, as a user, but it's very powerful. It's a very powerful tool. Why the tomogram sizes are different? Okay, that's a very good question. That is basically a bug. I'm sorry to recognize that. As Carlos said at the beginning, we are under development. It's corrected somewhere, but we rather prefer to have a stable version for the course, but it should be the same size. Basically, what is happening is that you're rotating your images where you are not rotating the reconstruction area. You have a vertical image and reconstruction like an horizontal image, so that's why you are missing information and dimensions doesn't match. But should be the same, because at the end the information it is what it is. You should be the same. I don't know if we have finished. Does Tomo 3D support fiducial free alignment? I don't know. I think not yet. I know the programs are there, but I don't know. Okay. So we have the lunch program at 12:30. Sorry, we have been a little bit optimistic with the timing, so we had no time to see any manual approach with fiducial with movies in tomography. I'm going to ask you for do 2 more steps and steal you a couple of minutes from lunch. I'm sorry, and in case we have time at the end, we can see a little bit about eTomo inside. So if everyone is finished, it's okay. If it hasn't finished, let it run because it won't bother us. And I'm trying to be fast but communicative. Well, for those of you who come from the HPA world, you are for sure familiarized with the movies concept. But basically, movies are the real acquisition procedure, where instead of taking one shot or one image, one photo of a projection, you have a bunch of them, and then you align them. And why is this done? This done, first of all, because it improves the signal to noise ratio, and this is something, especially in tomography, important because we do not have that much. We have very noisy images. And the second reason is to correct the motion. Think that when you radiate the eyes will deform, will make like a dome, and this moves the particles from size, apart from the actual movement of the particles. So that's why we need to align those movies, and the output of this alignment would be the tilt series that we have imported at the beginning. Okay. So we will execute just a couple of protocols, and I promise you we will be fast in lunchtime. Okay. So please go back to your Cypion environment, and as in the previous step, we are going to, as in the previous workflow or pipeline, we are going to import, but in this case, we are going to import movies. Okay, so here, if you see, we have Tomo import tilt series, but now we are going to import tilt series movies, which is basically a tilt series, but instead of images, we have a stack of images. So we have sets of stacks of images. Okay. Is there any question? Okay, so the procedure is very close to the beginning, to the one performed at the beginning. We are going to data day one, and instead of the first one, we are going to the movies folder. Okay, here we have a movie, a set of movies. We have a stack of images at each angle, and we are going to select this folder. Is there any question? Okay, sorry. We are going to select this folder, and as in the previous case, and I really encourage to do so, I insist, we are going to work with MDoc files. So we ask Cypion to read all the information from the MDoc. And this, for example, what we were talking about missing incomplete information in the MDocs. For example, this MDocs has no information about the dose. We are not going to use any dose tool here, okay? So I'm going just to set it to 1. You can set it actually the value you want. I look for it, but I don't know the exactly dose for this acquisition. But just set it to 1, and let's go over it. And anything else is needed, so please click on. Opa, sorry.
Yeah. You are in a frame, not in a folder. Yes.
We have to deselect the folder. If you select a file, Cypion will complete with the file. Select the folder, not the file, and the MDoc, the asterisk MDoc keywords. And let's click on execute. And now we are going to align the movies. For you familiarized with SPA, for example, you will, I'm sure you know Motion Core. For those of you who doesn't, it's basically performing the step we were talking before about aligning all these movies stacks. And we just search for it. If you search Motion Core, we have 2 programs, the one from SPA. Now we have the movies, so align tilt series movies. And let's open it. Is everyone here? Will the dose value not be in the text? For those MDocs, there is no dose information. And this is something that you might be able to deal with, because not always the whole information is complete. MDocs is for sure the best source of information. It's the most complete, but sometimes there is some information missing. I don't have experience in acquisition programs, so I can't tell you exactly why this happens. But the truth, it happens. Well, here in the Motion Core, is everyone here? Has everyone imported the movies? Will those value not be in the end? Sorry, I already did that. The import protocol says does not provide extra info. What?
I was not able to import the movies yet. Sorry. Because I was in another room, so I kind of...
Okay. It's okay. Just look for it here in the import section. And double click on it. Did you locate it? Okay, I guess you located it. And
so I was able to find the Tomo import tilt series. Then I went to day 1, so data day 1 and TS movies 10.3.
10.364, yeah.
Genau, exactly. The pattern asterisk mdoc again.
Okay.
And when I put execute, it tells me it can't find the voltage.
It's tilt series or tilt series movies?
Tilt series movies.
MDoc cannot locate. I don't know. Same problem here. I don't know what could be happening. So is your path okay? It's your path a folder, because sometimes if you click on one, I have another. If you click on sometimes if you for some reason click on here and say select, it will append at the end the file name, and you don't want this. You just want the folder path. I don't know if that's your case. The end should be tilt series movies 10.364. Yes, same kind of problem here.
Now I just clicked the folder above, and now it's saying no mdoc files were found in the introduced path.
Okay.
Since there are several people, they can join me in the room 1 and try to see what's going on. With
I think it might be something. Maybe did you set the dose at 1? It must be something related with the options, with the input options.
The initial dose to 1.
No, the initial dose to 0, the dose per tilt image 1.
Now it's working, yeah.
Okay. Now is it working for everyone? Is everyone fine now? Yeah, I know it's confusing, guys. I'm sorry, but it's just because these mdocs files has no information about the dose. I'm sorry about that. But I think this was beautiful data. That's what we selected it. Okay, so if everyone's fine, you should be able to click on execute, and everything should be okay. If anyone has any problem, please let us know. But if everyone is there and you have this protocol executed, now let's go to Motion Core. Search for it, okay? And be sure that you are selecting the tilt series movies option, not the other one, okay? This protocol, we are going to leave everything as default. So just please select the import set of T series movies that you already imported, and just click on execute. It will hang down this.
I don't hear you anymore. Sorry.
Sorry. Yeah, I know we are late for lunch. I just want to leave this executing, and we can close the morning session. I'm just, if the binding factor, leave it at 1. Don't in this protocol, please do not leave everything as default. Just input your T series movies. 126 steps, yes. Yeah, we are. If you have it running, please go launch it. If you have any problem, just let me know, because this is the last thing we are going to do in the morning. Do we need? I think it's an hour for lunch, right? 1:30. 1:30. I'm sorry. I stole to you 10 times of lunch. I'm so sorry, but I wanted to leave this running. So please, if you have it running, just you are free to go. And if you're not, let me know, please, and I will help you out. Thank you very much, guys. I don't find movies to import. Okay. I mean, Pablo, if you, I can do it, but if you want, maybe for him to share the screen, it's easier. I'm glad you like it. I'm really glad you like it. Welcome back, everybody. I hope you enjoyed your lunch. Okay, so now we should follow the workflow through manual alignment, but we miscalculated the time. We have been a little bit optimistic. I'm sorry about that. So we are going to move to the second session, driven by Jose Luis Vilas. He will talk to you about CTF correction, estimation, 3D reconstruction considering the CTF. And if we have time at the end, we will resume with the manual approaches for alignment. But I think it's more interesting for you to see the whole view and pipeline rather than focusing on alignment and reconstruction. So thank you very much. If someone can give him the control, because I'm presenting now, but
yeah, I need the control. Okay, I have the control. So, well, good morning or afternoon, everybody. I'm Jose Luis Vilas. I work as a developer of CryoEM, Electron Tomography algorithms in the Jose Maria and Carlos Oscar lab. And I'm going to show you how to estimate the CTF and how to correct the TIL series to achieve CTF-corrected tomograms. As Federico said, in this part of the workflow, oh, sorry, I'm not sharing the screen. Now, can you see my screen? Yes.
Yes, now.
The initial plan was to show you how to work with eTomo inside Scipion, and that's the reason why we imported the TIL series movies and we corrected the motion. And now Federico was going to explain you how to use eTomo inside Scipion, but instead of that, we will continue with the CTF correction. And later, if we have time, we will come back to the eTomo processing. So let's start with the CTF. Up to now, what we have seen is
the green side, green part of this workflow. So we imported the till series, or alternatively the movies. We correct the X-rays that they look like peaks in the images. Then we apply a dose filter to take into account the radiation damage. And we resample. Resample is not mandatory in our workflow, but we did it in order to speed up the computational time. And then we apply the pre-alignment with the X-core of IMOD. We seed the fiducial model, and we align the fiducials. And finally, we reconstruct using the GGSoft, that will be called Tomo 3D with the CERT algorithm, and also with IMOD by means of the weighted back projections. Now, in this part, we are going to estimate the CTF, correct it, and reconstruct the tomograms with the CTF. To put or to have a bit of context, when we acquire the image has imperfections. They present imperfection due to two effects. First effect is the diffraction.
Vilas, sorry, could you switch the presentation mode?
Yes, sure. Whoops. Good. So,
thank you.
You're welcome. So the images are not perfect, and these imperfections come from two different origins. One is the diffraction, that it's something intrinsic to the interaction radiation matter, and we cannot avoid that. We have to accept it. And the second one is errors or imperfections in my microscope that can be the aberration or the focus. We separate the focus and aberration because they are different things. The focus is a kind of error of the experimenter, and aberration are imperfections of my instrument. But in CryoEM, we introduce the focus in purpose. So the CTF describes the microscope behavior. So what happened? So we have an object, and the object diffracts different rays. They are here with different colors. So they try to represent the different wavelengths with short wavelengths. That is the blue. The red is a greater wavelength. And the lens convert all wavelength towards the focal plane. But if we modify the position of the focal plane, then the image will be the focus. But if you can see how larger wavelengths are in the outer side, and shorter wavelengths are in the inner side. So, sorry, in the opposite direction. The shorter are farther, and the greater are close to the origin. Mm-hmm. And this is the reason why we obtain the rings. These are the rings of the CTF that corresponds to the diffraction effect and appears as a consequence of the focus. So this is because in the focal plane, we obtain the Fourier transform of the image. So this rings appears when we compute the Fourier transform of the image. So how can we obtain the CTF? Well, we can carry out the Fourier transform of the image. This is what the CTF method does. And CTF is obtained by the periodogram technique, and there are other techniques. I think Amit Singer uses multi-tapering and different techniques. But summarizing, they compute the Fourier transform, and the Fourier transform, the absolute value raised to square is the power spectral density, the PSD. So from the Fourier transform, we obtain the rings. And the orientation of these rings is what will tell me the information about the focus and astigmatism, as well as the other kind of aberrations. So now the question is when we should estimate the CTF. Take into account that any kind of transformation we carry out can change my image. So we should estimate the CTF with the raw image. That means with images without alignment, without any kind of filtering, no any kind of transformation, just raw image. Think that if I apply an alignment, I can introduce borders because as a consequence of the rotation or the shifts, and that change the spectral properties of an image. So it should be estimated with the raw image. So we will estimate it with the imported TIL series. Okay, and in Cypion, we have different tools, different protocols to estimate the CTF. So we have IMOD, we have GCTF, we have system with CTF find, and we have IMOD. You can find the CTF methods in the left side panel in the TIL series CTF. You can see all these methods. So let's go to the Cypion project and let's start to the CTF estimation. As I say, the most important is we want to estimate the CTF with the raw image. So the raw image comes from here, from the import. And now I need to use a protocol that estimates the CTF. We can go to here to TIL series, select CTF, and we can choose, in fact, we are going to use all of them in order to compare and take the best one. In this case, we will use GCTF. So by double-clicking in GCTF, I get the GCTF form. And in GCTF form, the first is the input of TIL series. The input of the TIL series is the first TIL series, that we have. Is the first one is the import. The raw image, no alignment, nothing, no transformation. So we select it, and we can apply a downsampling factor. It doesn't, if the estimation is not, sometimes it's complex to find the rings, and you can visualize the rings much better if you apply a downsampling factor. So you can modify this downsampling from 1 to 2, 1.5, whatever downsampling you want. In this case, it's not necessary, but we are going to modify the box size to 512, and that means the size of the box where the Fourier transform will be computed. Due to the size of the image, this size shouldn't be greater than your image size, but in this case we will set 512. Regarding with the resolution, the maximum resolution will be 4 Armstrong. That is the outer ring in our of the dome rings. Due to our sampling rates 1.33, Nyquist will be 2.6. So a maximum resolution of 4, it's okay. And the rest of parameters, you can put it as default values. If we click in advanced, you can say unexpected tolerated astigmatism and different parameters. In advance, everything is, we can set everything by default, no phase shift, and the extreme is okay. So most of the CTF protocols can be executed by using default parameters. They are not, do not require anything else to do. And just remember, if you have any doubt about this, you can click on the help, and it will explain you the parameter and what its parameter does. Also, if you click here in help, you can go to the website of the plugin and you can find more information about it. And if you click on cite, you have the reference of the protocol if you want to cite it, or you need to find more information about what it does. So let's execute it. And now GCTF has been launched. If you click here in the output log, you can see the command that was launched, and information about the processing will be shown. No questions so far. So, okay, now we are estimating the GTF, the CTF with GCTF. But we can use other protocols. For instance, we want to estimate it with system. So system, you can find system or CTF find for in the left side panel, and again until series CTF, and double clicking in system CTF find for. Yes, the question about was the GPU set to 0? Yes, you can put the CTF to 0, and that's the number of GPU that you want to use to execute the CTF estimation. If you have multiple GPUs, you can put 0, 1, and they are the number of the GPU that will be used. And 0 is the default one. So if we return to system, let's open the form by double click. And this is mostly the same form that GCTF. Again, we have to fulfill with the input of the till series. And what's the input of our till series? The raw image. And the raw images are the imported till series. So let's select the imported till series. Select. The box size, we say 212. It's okay. We can put other box size if we want, but let's keep the 512. And the rest of parameters are correct. You can see the advanced parameters, but no phase shift, and the same as always. And we can execute it. So now, as you can see, GCTF ended, and system is computing the CTF. Meanwhile, system is computing. Let's check the GCTF results. We select the box, we go to the summary, and as always, here in the lower part of the main screen, you have the summary with the input, the raw image, and the output. The output is a set of CTF Tomo series. I can make click in Analyze Result, and a viewer appears with the status of my estimation. Note that we have 3 till series images, and the output is 3 CTFs. And here in the window, I have 3 CTFs. The status means that the estimation seems to be correct. Scipion has a criterion to decide if the estimation seems to be correct or is not correct. But this criterion might not be fully perfect. So that means if the status says that it failed, probably the till series has a kind of problem. but perhaps you want to estimate it with other method or other parameters. If I click here in the yes, Dimitri, the 5 Armstrong force system is correct. And if the CTF looks a bit different, perhaps you can check with someone, but just check that the parameters you use are the same I use. They should look like the same curves. Okay, now we have here the CTFs. If I click here, check where my mouse is, I can open the list of images. And this tells me the focus, U and V, for all my images, as well as the resolution estimated for each image of the TIL series. And this happens with all the TIL series here. And in the right panel, you can see the estimation of 2 things. First, in red, you can see the defocusing U, in blue, the defocusing V, and the difference between them is the astigmatism. Note that the defocus is around 2,700 nanometers, so is more or less correct. This distance is in Armstrong, and more or less the focus is quite stable. This happens for all TIL series. They are in the same range. If you know the information about the focus that was used to acquire the image, you can check this, the focus is correct, this the focus is not, so perhaps I have to remove this TIL series because it doesn't fit or it doesn't suit to the acquisition parameters. So system continues estimating, and meanwhile we are going to use IMOD estimation. Yes. Sorry, Sinsula. The estimation of U and V are the horizontal and vertical defocus. You know that the defocus is a measure of the astigmatism. The horizontal and vertical components have different defocus, and that's the astigmatism, that you have 2 orthogonal focus. And if the microscope is astigmatism-free, the focus should be the same, and the astigmatism that is measured as the difference between them will be 0. But if not, there will be a difference between them, and that's the meaning of the focus astigmatism. Let's continue with our CTF estimation. Here in the TIL series, CTF, IMOD estimation auto. With IMOD, we can estimate the astigmatism in 2 ways. First way is in automatic mode, and the second one is in manual mode. Let's use the automatic mode. So if I double click, I open the form, and in the form, as always, I'm going to use the raw image. The raw images are the imported ones. So I've already selected the imported ones. And now I have a lot of parameters. For instance, the focus tolerance, the expected defocus. I think we know from the acquisition, and you can check the m.dot file, but let's set the expected defocus value as 3000. If you check the GCTF, fact, we are going to check it. The defocus is around between 2,000 and 3,000. So let's set as 3,000. Think that these numbers are in Armstrong, and IMOD works in nanometers. In Scipion, we try to keep as much as possible the same units and the same inputs than the original methods. So that's why one protocol can work in Armstrong and the other one can work in nanometer. But internally, Scipion has a CTF model that will convert one, will have a standard model for storing the CTF. So that's why we can change from one protocol to the other and then correct the CTF in a later step. But in this case, the important thing is that we can set expected defocus close to 3,000 nanometers. Okay, let's come back to our IMOD CTF estimation and 3,000 nanometers. These two parameters, the angle step and the angle range, are a bit tricky. The angle step says that I'm going to estimate the CTF every 6 degrees. And the angle range is that perhaps my tone rings are not very visible. So I'm going to average all those images that are in a range of plus minus the angle range around the tilt image I am estimating its CTF. So here we can put 12, a number of 12, 11. It's that number for which the sign is close, the sign of an angle is close to the own angle, so that's a very good approximation. We are not going to estimate astigmatism, and the rest of parameters like cutoff frequency, no, and phase shift, no. And with these parameters, we can execute. I don't know if there's no questions so far, so let's execute. Probably let me know if you have the GCTF and system, the result of those protocols. And meanwhile, IMOD is estimating the CTF. Let's check system. CTF fine. Again, the input is 3 tilt series. The output is 3 tomo tilt series. So that's good. We can make click on analyze results. And oh, surprise, that CTF fine tells me that the first one failed, the second one failed, and the third one looks okay. Question of this is why? Well, here you can see why. In the first one, the tilt series 320, see the focus value. The focus value for most of the image seems to be in the correct range of 200, 500 nanometers, but in the extreme tilt angles, for the extreme tilt angles, CTF fine was not able to estimate it properly. So that's why Scipion says, okay, the status failed. Perhaps you can remove those tilt images by means of the protocol exclude views that we didn't show in this tutorial, but when you have this kind of behaviors, perhaps you can try to do those things. Alternatively, the tilt series 48 also present the focus in the same range, but the negative and extreme image present a weird behavior in the tone rings. So it seems that CTF find was not able to estimate it. However, the last one looks okay, and the range is around 2,500 nanometers, and is in the same range that GCTF. So at least we can trust in the estimation of the third TIL series. The other ones, GCTF seems a good estimation, but CTF find, in this case, the result is not what we expected. But this is the good side of Cyprian, that you can combine different methods to estimate the CTF or estimate the reconstruction or whatever you want, and choose the one you want. And let's check what happened with IMOD. But before yes, good. But before launch IMOD, let's end with eTomo. So again, let's go to eTomo CTF estimation, double click, and we have the form. So which parameters? The TIL series. We know that the CTF must be estimated with the raw image. No alignment, no transformation, nothing. So we select the imported TIL series, and the eTomo works in microns. So this range is okay, and the phase shift we have to modify because we don't want to estimate a phase shift. So let's put a phase shift from 0 to 1 degree. That 1 degree is almost no phase shift, and with a step of 1. In this case, eTomo works with a tile size or a box size for computing the Fourier transform of 256. It's okay, and we can click on execute. So let's execute, and while eTomo is computing, we can check the IMOD results. So let's click on Analyze Results, and IMOD says that the 312 it's okay. The 48 looks that it failed, and if we check the focus range, that's true. Doesn't look correct. And the last one, 293, Cyprian predicts that it's okay. So what we can say from this is that the third TIL series looks okay for all CTF protocols. The second one seems to have problems. So perhaps the second one, we don't want to work with a TIL series that present problems for different algorithms. So perhaps we want to do a subset with that. Let's see what the eTomo says. But I know I have to show the protocol.
Okay.
This is because some of you asked it about the protocol parameters of eTomo. The most important is the phase shift, that we are not estimating phase shift. So that's why we put a phase shift of 0 degrees to a maximum of 1 degrees in steps of 1 degrees. If you put 0 and 0, eTomo fails. That's why we put a ridiculous phase shift. 1 degree does not affect. And should be more or less quick, the estimation of hematoma. Let's wait a little bit to see if there's questions. Well, just as a comment, one interesting thing is that normally the workflow is has a shape of column, but here in Scipion, because we can estimate the same step with different tools, we have a kind of tree with different branches. Instead of vertical, it becomes more horizontal. But at the end, what we are going to do is to correct the CTF. And to correct the CTF, we have to select one of these 4 alternatives. And we will choose the best one, or what we consider that is the best one. No, Sinsula, we don't have to accept that till series output only if the status says that it's correct. Perhaps we can still work with the ones that doesn't look correct. Just the Scipion writes a recommendation. This, for me, this present the focus range that doesn't seem to be correct, but the user can use what he wants. Well, eTomo is working with the last one. You can see that in the output log. How? Because it computed 84 nets, it computed 293, and now it's computing the 3rd till series. So it will finish soon. Well, meanwhile, eTomo is computing the CTF estimation. I'm not going to explain you how to use the CTF estimation of IMOD in manual mode. That will be explained in the 3rd day. But let me open to show you just very quickly, meanwhile eTomo ends. You also can use a manual estimation of the CTF here with IMOD, so double click. And if you see, this form is exactly the same than the form of IMOD automatic mode. But now, as soon as I may click on execute, it will open a CTF plotter from IMOD. So let's put the input. The input is the row till series, and it doesn't matter these default values. We can set the same that I put before, 300, and angular step of 12, angle of 12, this was 6. And don't worry if you don't follow me now introducing these numbers. We are not going to execute the CTF in manual mode. Just this is for your knowledge. Meanwhile, IMA is executing. So once I introduce the till series and some expected parameters, I can make click on execute, and a window appears. So I can select and make click in the till series. And by double-clicking the tilt series, CTF plotter from IMOD is open. So now I can estimate manually the CTF with the CTF plotter as you do in eTomo and IMOD. And you can select the number of zeros, you can apply a downsampling, and so. But we are not going to estimate the CTF in this way. Check that here you can see the radial average of the tone rings, and the focus is estimated in this table. And I would carry out this tilt series by tilt series up to estimate all of them. But we are not going to explain to you now the CTF plotter. This will be explained in the third day, the third session. Okay. Now I'm going to delete this box, the manual CTF estimation, because we are not going to use it. So it's deleted, and eTomo end. Yes, to open CTF plotter, you have to make click on execute in the CTF manual estimation, but you will see that in the third day. I prefer now will be focused on the automatic estimations of GCTF, system, IMOD, and eTomo. So let's check the eTomo results. So if we analyze them, all of them are okay, and the range is nice. So it's around 2,500. So that's good for all tilt series. So eTomo does not present any kind of problem in the CTF estimation. So what we have seen up to now, we've seen that GCTF says that all of them are okay, and we like the focus range. It's around 2,500. And eTomo also has a good CTF range, around 2,500, and all of them are okay. However, system and IMOD presented problems. In particular, we saw that the 48 failed, and we don't like the resolution range. So what can we do now? We can say, okay, let's take the GCTF estimation or eTomo estimation, because they are the ones that look correct. Or we can say, let's create a small subset, and let's remove the tilt series 48. In a normal image processing, I wouldn't remove any tilt series, but I'm going to show you how to remove a tilt series here, because this is a course, and I would like to see how to remove a tilt series and work with a small subset, removing the bad CTFs. So we're going to work with GCTF, and we're going to create a subset. So let's click on Analyze Results. These are the results of GCTF. And we say that the number 48 presents some problems. So let's remove it. To remove it, just we mark the tilt series in black, and we may click here on Generate Subsets. The meaning of 2,500 is the focus, is the position of the sensor respect to the focal plane in the microscope. That's the meaning of the focus. in CryoEM. And 2,500 is the distance in nanometers. And here you can see the distance in Armstrong. That's why it has one order of magnitude more. Okay, as I said before, this is the viewer of GCTF. If you miss it, just click on Analyze Results, but first selecting the GCTF box, Analyze Results. And in Analyze Results, we have the 3 CTFs in with the status in OK. We want to create a subset. We say that the number 48 is not the one that we want. Why? Because other CTF algorithms say that have problems to process this one. So to remove it, just mark it with in black. Check if you are. I would like that everyone now see that I mark it. If you are out or miss it, see that I mark it. And now I generate subsets. It was removed from the list. Now it's not here, but I close the window and I go to the summary. And in the summary, it says that I have 3 outputs. One output has 3 CTFs because GCTF generated 3 set of CTFs. The second output has 2 items, the good ones. And the third output is the one I remove it, the one I don't like it. This is the 48. We will use the second output, the one with 2 CTFs. Okay, so let's work with this one. Now, what happened? I have 2 CTFs, but I have 3 till series that we used to align. Is this one. Remember that we have the normal ones and the interpolated. The interpolated are used to visualize the alignment, but to process, we use the normal ones, the non-interpolated. So we want to do a subset of this till series, removing the number 48, because it's the one that we remove it in the CTF. So I'm going to do right-click and open with Data Viewer. See here, right-click on the till series of the fiducial alignment, right-click, Data Viewer. And I have the Data Viewer with all information of this till series. The till series 48 is the second one. Why? Well, here you can see the title of its column. If I go at the end, I can see the till series ID. So I'm going to move it.
Vilas, some people is asking in the chat to go back to the removing step because they have gotten lost.
Okay.
My screen gets stuck from time to time, and then it takes me a while to find back.
Okay.
And doing so, I totally lost the stream.
Okay, don't worry. Let's go to GCTF. Let's select the GCTF box. And let's click on Analyze Results. We have 3 till series. We put the 48, mark it with the black box. And then we click on generate results, generate subsets. It's fine for everybody so far?
Yeah. I missed exactly that step with generate the subsets.
Good. So now you should go to the summary, and in the summary you should see 3 outputs. The first output is the original output with 3 items. The second one has 2 items. These 2 items are the good ones, the good 2 CTFs. And the third item is the bad one. In fact, if you check the name, they are called good set of CTF, and the third one is bad set of CTF. So we will work with the second one, the good set of CTF.
I only have one output file in the summary of the GTF tilt series.
Have you make a click on generate subsets?
Yes.
I don't know if someone can go to.
I can check.
Yeah.
You are Tamara?
Yes.
Okay. I'll join your machine and check if what's going on. Okay.
Meanwhile, just to be sure that we are in the same page, we open the result with analyze result of GCTF, we mark it, and we may click on generate subsets. And as a result, we should have 3 output. The original with the 3 estimation, the one with the good ones that has 2 tilt series, and the one with the removed one that is the bad set of CTF estimations. And now what we are going to do is to select in the aligned tilt series those that are the good ones. I mean, we have 2 good CTF that corresponds to 2 tilt series, and now we are going to create a subset with those tilt series. Yes, Sinsula, we have to create the same subset in the fiducial alignment. In a future, we will provide a protocol that will do the matching between each CTF has associated a tilt series. So in the future, we will have a protocol that will carry out the automatic matching between CTF and tilt series. And if the CTF is not present, that tilt series will be removed automatically. But for now, we have to do it manually. I think that despite Scipion Tomo is still under development, and we can process in more or less from the beginning up to the end. Some small steps are still under development, like this one, and we have to do the manual matching between CTFs and tilt series. We regret that, but we are working. And if we want to create the subset of 2 tilt series, we go to the fiducial alignment. We select the tilt series, the non-interpolated, because one more time, the interpolated tilt series is only used for visualization purpose. So we select the non-interpolated, right click, and we open with data viewer. I wait at this point to be sure that everybody is watching. Good. So we open the data viewer. And here you have the 3 till series that we align. And we have titles in each column. So we have the size that tells me the number of elements, that the number of images that has its till series, the sampling rate of its till series, and so on. And at the end of this table, we have one column that is called till series ID. So this column of till series ID tells me that what till series we have. In this case, we don't want the 84. So we are going to remove it. How? We remove it by going to the first column that is enabled, and we unmark it. And then you do click on till series. Just one more time to be sure, because this could be a bit tricky. Fiducial alignment, then non-interpolated, right-click, data view. We don't like the second one. Why? Because the second one is the number 48. And we mark that till series. And we click in till series, the red button. So let's call it put till series. Just an advice. Every time you put a name to a box like this one, now I can close. And then the subset was created. Or every time you put a name in a protocol or you have to rename it, see that with the right button, I can rename whatever box. Avoid the use of strange characters like dollar, percentage, tilde, semicolons. Avoid all that kinds of symbols, because it can present conflicts with some, I don't know, steps of things that those symbols are not thought to work by many programs or whatever. Okay, now we have a good set of till series, and the good set of till series have 2 elements. We can make click, right click, and visualize them with the IMOD viewer. The window with the list of till series is open, double click, and we can visualize it in IMOD. So this is the till series. And we see some kind of fluctuations because this is the non-interpolated one. But despite it's the non-interpolated one, it contains the information about the transformation matrix. Okay, now we have 2 till series with an associated interpolation matrix and 2 CTFs. So what we are going to do now is to correct the CTF. And to correct the CTF, we can use IMOD CTF correction. So we go to till series, CTF, IMOD CTF correction. So IMOD CTF correction asks the input till series. What's the input till series? The subset that we already created. So let's go into select it. And what's the input CTF estimation? So it's the one from GCTF with 2 items. So I have many CTF estimation things that this is something really nice, at least for me, of Scipion. Scipion, these protocols ask CTF. So when I do click here in the lens, Scipion only show me the CTF objects. There's a lot of objects like till series movies, but because the input of this protocol is a CTF, Scipion only shows me the CTFs one. And I want the one with 2 elements that is the subset of CTF till series that we created. So we select it and execute. This is the default parameters of IMOD that we are not going to use. I said before that Scipion has its own CTF model that allows the conversion from one protocol to the other. So despite IMOD works in nanometers and GCTF works in Armstrong, internally Scipion converts the units and the model from one output to the input of the next one. So you don't have to be worried about units and conversions. Let me check the chat. No, if you use the 3 CTF estimations, the protocol, I didn't try, but it shouldn't fail. But here in the IMOD CTF correction, you have to make sure, and this protocol will fail if the number of elements of the input till series and the number of CTFs is not correct. They have to have the same number of elements, the same number of till series, and the same number of CTF estimations. Both must be equal. Yes, I can go slower. Okay, if I understand you, or I guess you probably was lost here, that probably you have the subset with the till series, and now it remains the CTF correction with IMOD. So the only thing I did is to introduce the input till series and the CTF estimation. The input till series is the boot set of till series. That is the one we created. And the CTF estimation is the one with 2 elements in the subset. The number of elements of the till series must be equal to the number of elements of the CTFs. Otherwise, the protocol will complain. And the result, we can make click, right-click, analyze with IMOD viewer. We can visualize it. And the images are CTF corrected, and they doesn't present any kind of ringing or artifact that could be result of a bad CTF correction. So that's good. And what's the last step? Well, the last step could be the tomogram reconstruction. If we want to reconstruct the tomogram, we can do exactly the same we did with IMOD and or Tomo 3D. In this case, we are going to use IMOD tomo reconstruction. So we are going to reconstruct the tomogram with the CTF corrected with IMOD. How? Well, let's go to tomogram section, to tomogram reconstruction, and we select IMOD tomogram reconstruction. So let's do double click here. And what the protocol asks is the input set of till series. So the input set of till series will be the output of the CTF correction. The output of the CTF correction is here and is a set of till series. This set of till series has the CTF corrected. So we're going to select it. Okay, there it is. And what thickness we put before? We put a thickness of 300. And we can reconstruct now, but let's take advantage of this reconstruction to show something. Let's make click on advanced parameters. In the pixel size difference, oh yeah, you mean the pixel size difference because we computed the CTF without binning, and the no, the CTF it's the focus. So the focus is measuring nanometers or Armstrong, but so binning does not affect, because if you apply a binning to compute the CTF, that for instance GCTF has a downsampling parameter, the result of the downsampling will tell you the focus. The focus will not change with the downsampling, so the result will not affect. The focus and astigmatism are invariant under binning transformation. And okay, so let's reconstruct the tomogram with the CTF corrected. Previously, we used also IMOD tomogram reconstruction. And we say that IMOD tomogram reconstruction uses weighted back projection. But we also see that Tomo 3D, it means Chichisoft, that the name of the plugin will change, use it SIRT. So in this case, we are going to reconstruct. Let me put you here both protocols at the same time. In the left, you can see the one we used it before, and here is the one we are going to use now. So we are going to put a SIRT-like filter in order we saw that the SIRT reconstruction present more contrast than weighted back projection. So now what we are going to use is to reconstruct using a SIRT filter that will emulate the result of a SIRT reconstruction. So let's go to change the name, put SIRT like. SIRT like. To change the name, just make click on the pencil and you can write the name. Okay. And we put a SIRT filter of 25 iteration, and we click on execute. So now we will reconstruct the tomogram with a SIRT-like filter.
Excuse me, José Luis.
Yes.
Could you repeat this last part again, please?
Yes, sure. Previously, we reconstruct the tomogram using weighted back projection, and we obtain a tomogram with IMOD. You can see here, and we compare the tomogram with the SIRT result of Tomo 3D. You can see here the virus. But you can see how the contrast is not, you can distinguish that the virus is there, but you cannot visualize, for instance, the spike of the virus. However, when you use the SIRT algorithm of Tomo 3D, we were able to visualize the spike. So let's open. So here you can visualize that the virus presents the spikes. So what we are going to do is to reconstruct again with IMOD, but using a filter that simulates a SIRT reconstruction. So Tomo 3D, that is ggsoft, uses the SIRT algorithm, but Tomo reconstruction of IMOD uses weighted back projection. So in this case, we are going to use IMOD simulated a SIRT reconstruction by means of a filter. And we do that by setting the number of iterations of a SIRT filter. Originally was 0, but in this case, we set it to 25. And
sorry, but I don't understand, where have you started with this process? So which is the input of this?
The is the CTF corrected.
Okay, so you click in the CTF correction finished box, right?
Exactly.
You click, okay. And then?
No, okay. I'm going to do it again.
Thank you.
We want to reconstruct. So because we want to reconstruct, we go to tomogram section. In tomogram section, we go to tomogram reconstruction. And we want to reconstruct with IMOD. So we open tomogram reconstruction of IMOD. And now we select the TIL series that are the result of the CTF correction. So we select IMOD CTF correction that has 2 items. So we select it, and we have to select a thickness for the tomogram, and we put 300. We put also 300 in the others protocols. But in this case, I say that instead of using only weighted back projection, we are going to add a SIRT-like filter that will simulate the same behavior as a SIRT filter. So we are going to put 25 iterations for the SIRT filter. And then we click on execute. So far, so good?
Yeah, perfect. Thank you very much. Okay.
Okay. Now, I go with your question, Roberto. Let's check the reconstruction. Let's analyze results. And now we see how the effect of the SIRT filter allows to visualize the spikes. And this result is much, much closer to the original method of SIRT that we use in Tomo 3D. Okay. In this case, what we have done. Let's to summarize what we did. We estimate the CTF, and we create a small subset in the fiducial alignment. And then we took the subset with the CTF and the alignment. And then we correct the CTF and we reconstruct. This CTF correction consider astigmatism. And this is the Roberto's question. However, the astigmatism was measured here with the tilt series in a non-rotated position. However, when we apply the alignment, the images are rotated. So our CTF estimation was not fully correct in the sense that the astigmatism is not in the same position than the tilt series. It was my mistake. I should tell it before, but we will fix it right now. The thing is, here you can see tone rings in this presentation. These tone rings are tilted, but the CTF, the original images were not aligned. So the astigmatism, the axis of these rings are horizontal and vertical. It means perpendicular to the edges of the image. However, when sorry, I lost the window. However, when these images are aligned, so they are rotated. We have to put the CTF in the same position than the image. And we do that by rotating the astigmatism. How to do that? With xmipp Tomo astigmatism rotation. So go here to tilt series and xmipp Tomo astigmatism rotation. Chunjang Wang, does this mean Tomo 3D has considered CTF correction? Why Tomo 3D provides a better contrast? Well, no, Tomo 3D does not consider CTF correction. In the left column of our image processing, we did not consider CTF correction. But Tomo 3D uses an algorithm that is SIRT, and IMOD uses other algorithm that is weighted back projection. They are different algorithms. In fact, if you want to see the difference, there are many algorithms to compute the reconstruction. For instance, the most important are weighted back projection and arithmetic reconstruction, ART and SIRT. These last two are algebraic methods. In Scipion, we have different algorithms. In IMOD, we have weighted back projection and SIRT-like. SIRT-like try to simulate the same result than SIRT, but it's a different method. In Tomo 3D, that is GGSoft, the name will be changed. You can reconstruct with weighted back projection or with SIRT. the result will look different. The tomogram is the same, but it looks different. Perhaps you have more information of some frequencies than in the other, but because they are two different methods of reconstruction. Also, we have eTomo that allows you to reconstruct with weighted back projection with SART. And eTomo that I cannot tell you which protocol, which algorithm it uses. And if you want to know the difference, weighted back projection considers that its image is the projection of the sample. And in the reconstruction, we want to combine those projections to get the 3D. But when I back project those projections, you can see how here in the intersection, the low frequencies dominates. And I have a kind of artifact. But if you see the object, my object is a circle. But here I have a kind of star, and the low frequencies dominates in the reconstruction. Filtered back projection consider that I'm going to apply a filter in the projections, and then when I will back project, I will avoid this domination of low frequencies to recover my image. In contrast, ART and SIRT, they consider a kind of linear equation system in which along its direction, its projection direction, for instance, we have here the horizontal and vertical ones, are when we project, what we do is to zoom all pixels. We discretize or we create a kind of net or matrix that is what we want to know. And this first pixel is the zoom of the first row. The second pixel is the zoom of the second row, and so on. And the same happens with the columns and other directions. So at the end, what this algorithm does is they consider a linear equation system. And the difference between them is how this system is solved. So they impose some constraints, like the difference between the projection and the image should be minimum. So they consider a kind of it's a kind of optimization problem. That's the reason why they achieve more contrast. But the price to pay is a lower convergence and therefore more computational time and higher computational burden. That's the difference between those methods. I don't know if that casts light on the topic. So far, so good, because I don't know if Sinsula, you said something or you are... Yes, I said astigmatism rotation, but with something different to the reconstruction. So in this first part of the workflow, in this first column, we did not carry out any kind of CTF correction. In this second part of the workflow, we are considering CTF correction. But what we didn't do is to correct the astigmatism. To do the things properly, because I'm sorry, I commit a mistake, I'm going to remove these two, and I'm going to start from this point. So now everything will be clear. The important thing is that this CTF was estimated with the original TIL series, but the TIL series in this point, this subset, consider the TIL series, but the TIL series is rotated. So we have to put the tone rings or the CTF in the same position than the image. If my image are rotated, my CTF must be rotated. And that rotation comes from the astigmatism. That's what we are going to do. To correct the astigmatism, we use xmipp Tomo, that is here in the tilt series CTF. And we have to put set of tilt series from which get the transform. So we need a tilt series, and the tilt series is the good set of tilt series. Is the aligned ones, but the subset. We select it. And we also need the input tilt series with the CTF estimation. And use the set of tilt series with the good CTF that has 2 elements. We cannot use the corrected tilt series because that corrected tilt series didn't consider the astigmatism. If your CTF is free of astigmatism, then it doesn't matter. You can use those tilt series. But if your tilt series has astigmatism, you have to put the CTF in the same orientation than your tilt series. That's the reason why. In our case, due to the astigmatism of our tilt series is small, we will not see any kind of difference if we rotate astigmatism or if we do not rotate astigmatism. But to do the things properly, we have to rotate the astigmatism and put the CTF in the same position than the tilt series. And so here, let's click on execute. And now the astigmatism will be rotated. That's easy. And now that we have think that the output of the astigmatism rotation is a set of CTF, this set of CTF has the astigmatism rotated. So now my CTF is in the same orientation than my tilt series. So now I can correct the tilt series as we did before with the IMOD CTF correction. Yes, exactly, Pablo. The CTF is not applied at this point. Now it's when we are going to apply the CTF. Now that the CTF is in the same orientation than my tilt series, we can apply it. So to apply it, we go to tilt series, CTF, CTF correction. We did this before, but we delete it, and the input tilt series will be the good tilt series image. So we select it, tilt series image, and the input of tilt series CTF estimation will be the astigmatism rotation. So we select it, and we use IMOD CTF correction with default values. So now the CTF correction is launched and should be quick. Okay, now we have CTF correction. We can make sure, open the output with the IMOD viewer to see that it doesn't present a ringing or any kind of artifact that would indicate about CTF correction. And there's no ringing, so it looks good. Okay, perfect. So now it remains the tomogram reconstruction. And we will use IMOD tomogram reconstruction as we did before. So tomograms, tomogram reconstruction, IMOD tomogram reconstruction in the left panel. Double click, and it asks the input set of till series. The input set of till series is the IMOD CTF correction. Means the set of till series with the CTF corrected. So we select it. The thickness is 300. That is the same that we put previously. And as we did before, we are going to use a sealed filter with 25 iterations. So we make click on execute, and now we are reconstructing. Let's wait a little bit, and if you have any kind of question, please ask.
I can't. It's in the advanced, right? The point with the.
Yes, it's in advance.
Yeah. Sorry. Yeah. Found it.
It's 25 iterations.
So I have a question. The output now is binning 4, correct? And we put in a CTF correction fully, so at binning 1.
Yes, but the binning for the CTF does not. It doesn't matter, because the CTF, at the end, what you want to compute is the focus, the astigmatism, phase shift, the parameters that model your microscope. So those parameters belong to the microscope, not to your image. So
but at the end, I want to have again my 1.3 angstrom per pixel resolution. Or not?
Then, well, we are reconstructing now with binning 4, because otherwise you will need a lot of RAM memory, a lot of disk, and this is just a course and a tutorial. But if you want to reconstruct with your raw image, just remove this till series normalization.
Correct, but I will never come back from this workflow back to my full resolution, so 1.3 angstrom per pixel.
No, in this point, in that case, you will have to compute again this part.
Okay.
Without normalization. There's an alternative. I will show you in a few minutes an alternative, because here you use it. You have the alignment information. So one thing that you can do is to use this transformation matrix, it means the alignment matrix, and apply it to another till series. For instance, here you have the matrix of the alignment, so you can apply this matrix to the unbinned till series. But in this tutorial, we are not going to reconstruct with binning 1. But if you want, you can also apply this transformation matrix to the binning 1 till series, avoiding the fiducial alignment again.
Okay, thanks. Yeah.
To do that is in subtomogram averaging. This, I know this shouldn't be here, but it's here. Subtomogram averaging till series assign alignment. So in this protocol, you take a set of till series with a transformation matrix, and you can set the transformation matrix to another till series. So in this case, you will apply the transformation matrix of the fiducial alignment, and that transformation matrix will be set to the binning 1 till series. And that's how you can avoid the alignment. Otherwise, you have to align again. Okay. So now we have the IMOD tomogram reconstruction. And if to here right-click with IMOD, we should be able to visualize the reconstructed tomogram. As I said before, in the workflow that we deleted, because of the seared filter, we get a high contrast. And so we can see the virus, the capsid, with the spikes. Good. Okay, so now we know how to reconstruct a tomogram without CTF correction and with CTF correction. But something that we would like to have is to apply a local CTF, because the focus, when we tilt the image, the focus of the center of the image is not the same than the focus of the extremes of the image. So how can we do that? We can do that with Nova CTF. Thanks to Nova CTF, we can correct with local CTF correction. The idea is that its plane has a different defocus. For instance, the red point here in the sample has a different defocus than the green and blue points that are here in the bottom. And the same happens when we tilt the sample. The focus that we estimated with the CTF they are expected values for its tilt image. But we can apply different CTF corrections and select and infer the correct defocus for each position of the tomogram according with the tilt distance. And this is what Nova carries out, to combine different CTF estimation according to the position of the point of the tomogram. And this is what we are going to do now. So how to use Nova CTF? Well, we are going to here in the left side panel, tomograms and tomogram reconstruction. And we will use Nova CTF defocus. Note that we have two different reconstruction algorithms. The first one triggers the second one, but if it fails or something happened, we can open the second one by our own opening here in the left side panel. You will understand this now. So let's open Nova CTF defocus. Nova CTF defocus requires the input set of tilt series and the input CTF estimation. So what's the input set of tilt series? The input set of tilt series will be the good tilt series. So let's select good tilt series. Why we want to select the good tilt series? Because Nova is going to estimate the defocus of the local defocus. So the input must be a tilt series without CTF correction. That's why we select the good tilt series without any kind of correction. Nova will correct the CTF, but in a local sense. So we select, and the input CTF tilt series will be the one from IMOD, but with the rotated astigmatism. So we select xmipp tomo astigmatism rotation. So we select it. There are other parameters that are required. For instance, the tomogram thickness, that is 300 voxels, is the same thickness that we put in the rest of tomogram reconstructions. Let's put the focus step of 15 nanometers. And we can also select if we carry out a phase flip or multiplication. This is different types of CTF correction, depending on the sign of the if we take the absolute values or the CTF, or if we multiply by the inverse. And here we can select if we correct the astigmatism or if we don't correct the astigmatism. We are going to put that, yes, we want to correct the astigmatism. Why? Because we estimated the astigmatism and we rotate it. So let's set as yes, we want to correct the astigmatism. And the others are filters that we are not going to use, but that perhaps can be used. Okay, so this protocol takes a bit of time, so let's execute it. And you will see that in any moment, this box will be green, like now, and automatically a second box was launched. This is what I said, that Nova CTF has two protocols, the focus and the reconstruction. The focus automatically triggers the reconstructions. So in case of this one fails, I can open it here and continue. But if we use CTF the focus, automatically we'll launch the second one. And with this protocol, we end with the reconstruction of the tomograms. We will continue now with other things, but the reconstruction is done. Questions so far? I see your writing. Meanwhile, I think we had a break at 3:30. So I think because of Nova CTF takes a bit of time of up to in the reconstruction. So we can stop here for 15 minutes and continue with Nova CTF reconstructed. 10 minutes, sorry. Yes, we will check Nova CTF result later, and we will continue with how to evaluate the quality of the tomograms with local resolution. It's just that due to it takes a bit of time, I think it's a good moment to have a break.
Okay, so hello, everyone. I see there is some questions about the astigmatism rotation. I don't see if you are there, Antonio, or not.
Yes, I am. Hello.
Okay. So about the astigmatism rotation, the thing is that you do not want to estimate your CTF from interpolated data, because when you interpolate, most of the time you are suppressing high frequencies. So in the practice, there is not that much of a difference, but if you want to go to very high resolution, it's better not to do it. And then you want to align the series. So when you estimate CTF, also estimate for astigmatism. The astigmatism will be these two defocus values and the focus angle. And this defocus angle will tell you how astigmatism is rotated. And at the same time, then you are having your images and you are aligning them. So you are rotating them. So there is a mismatch between the rotation from which the series that you estimate the CTF from and the new aligned till series. So you want to match both of them. So you want to rotate the astigmatism. So if the series is very astigmatic, you might see a difference. But in the other hand, if the series is very astigmatic, you might you might want to discard the series if it's very, very astigmatic. So there is a trade-off. The workflow is planned to be as correct as possible in the canon of the tomography, but that's basically the reason why you want to rotate the astigmatism. I don't know if it's more clear now or not.
Yeah, no, thank you.
You're welcome. So about the dose filtering, the images, the binaries are already dose filtered. So I don't know if you mean dose filtering for estimating the CTF, but for the CTF corrected reconstruction, the images are dose filtered because they are going out from the fiducial alignment, and the fiducial alignment is performed over those filtered images.
Hi, Sinsula. The reconstruction without CTF, well, it's much better if you always reconstruct with CTF, but if you are going to carry out a subtomogram averaging, you will need a CTF correction per subtomogram in, for instance, Religion. I'm talking about Religion 3, not Religion 4. So in that case, your tomograms should be reconstructed without CTF correction, because you will correct the CTF in a later step per subtomogram. But if you are going to analyze a cellular environment, you will need a CTF corrected. You will see this not tomorrow. Tomorrow you will see how to pick, but in the third day you will see how to carry out the subtomogram averaging. Okay, shall we start? Okay, what we have done up to now. So now we know how to import the TIL series, correct the X-rays and the dose, and align the fiducials. And then with the aligned TIL series, we reconstruct. We also see how it's possible to estimate the CTF with different algorithms, and how to correct the CTF taking the best CTF estimation of all the estimation that Scipion provides. And we also know how to correct the CTF and reconstruct. Finally, we see how to apply a reconstruction with a local CTF correction by means of NOVA. Let's open the output of NOVA, the output of NOVA was 2 sets of tomograms, and by right-click and opening the IMOD viewer, we can see the result. Again, it looks like very similar to the IMOD reconstruction. One interesting thing about weighted back projection or NOVA CTF is like, well, if here I do Control X to Control X, you can see the different views. And now I can click on a fiducial and see how the fiducial looks like. So we can see how the tomogram is well aligned. The fiducial are more or less with an spherical shape and doesn't present a strange shape that is an evidence of alignment problems. So one important thing I would like to highlight here is, well, NOVA CTF tomogram, we don't see too much the capsid as well as the spikes, but it doesn't mean that the information is there. This information of the spike can be hidden by low frequencies, and perhaps I have to do a boosting of high frequencies to visualize them properly. It's something similar with the reconstruction of CIRT. CIRT let me visualize the information, but it doesn't mean that in weighted back projection the information is not there. The information is there, but perhaps it's not possible to visualize it with our eyes. We have to apply a kind of filter, blur by a Gaussian, to be able to visualize the spikes. So would not be surprised if you cannot see the spikes or the information. The information is there. Okay, so this is the NOVA CTF. No, we already started, Tamara. We just, NOVA ended, and we are just checking the result of NOVA. We didn't launch NOVA CTF. Just in the break, NOVA was computing. You can see the NOVA parameters. Sorry. You can see here.
I can't find the NOVA on my tree.
Oh, okay. Okay, you can launch NOVA in the left side panel in tomograms, in the section of tomogram reconstruction, and opening NOVA CTF defocus. So this window will open.
I have problems when I'm pushing a arrow button. It just goes either to the very end or to the very top. That doesn't make it easier.
Can you try, Tamara? It might be the remote way we are accessing the machine. Can you try clicking on the menu, the project menu, and then find, I think it's find all protocols, or
I mean, I now found NOVA CT tomography.
Tomography should be. It may have different names, maybe. Can you do it, Vilas, from the menu?
Yeah. Let's press Ctrl+F to open the search.
Sorry, Vilas. For no VNC, well, you can do it. I don't know. I have problems. Control doesn't work in my machine. I don't know why. But okay, if for everyone works, that's fine.
check if Control plus F.
It works, and when I can type in Nova.
Yeah. Open Nova CTF, Tomo CTF defocus.
Yeah.
And then this window should be open.
Yeah. But I already did that before the break, didn't I?
Yeah. So
but then it shouldn't then the job be finished and found somewhere in the tree?
Oh, yeah.
Okay. You mean in
okay.
And my tree is just very, very extended.
Don't worry. Look at my window.
Okay.
You see this icon?
Yeah.
Can you see my mouse?
Yeah.
Make click on this icon.
Okay.
It's reorganize the workflow.
Thank you.
Another nice tip is that if you push shift, the shift key, and then you do a scroll with the mouse wheel, you can make bigger or smaller the workflow. You can check that it's very useful sometimes to have a full view of the workflow. Let me see. Tell me if you can do it, please, in the chat or with your microphone.
Yeah.
Good. And other nice feature is that now all boxes are in green color, but sometimes your workflow is so big that you cannot find some boxes, and you want to work with different colors to put, for instance, the boxes, all protocols related with alignment in, let's say, yellow, or the imports in blue. So you can do that also. Probably I don't used to use them, also because this workflow is very small. But if you are processing with a big workflow, you will be using it, and probably tomorrow you will have the opportunity to see how to put the colors. You can find them here in project, toggle color mode, and you can change different colors. Now they are in gray with a green circle that says that it's working, and so on. But I prefer to work with them in green. Okay, so now that we have run Nova and we have all protocols, all reconstruction, we are going to estimate the quality of the tomograms. What we are going to do now, it takes time. So you have a tutorial about how to do it in the shared notes. In particular, I'm going to copy the link and I'm going to paste it in the Puppet. So here in this link, you will see the image processing that we are going to do now. And I will going to show you, and you can do it by your own, but the last step takes a lot of time. So that's why I prefer that now you just watch the workflow instead of trying to duplicate it or doing it. So you can go to the projects and you can open the day one alignment and reconstruction. So let's open it. And here you have a full workflow. So far, so good. Good. Okay. Now the workflow that you are watching now is the same than before. Things that we have the first column with the fiducial alignment, the tomograms reconstruction, the good tilt series, the astigmatism rotation, and everything. In this case, we computed NOVA without astigmatism rotation. So that's why we didn't use the astigmatism rotation before NOVA, because we didn't estimate astigmatism. Okay. And in the right side, we start with import Tomo tilt series. How to change projects? Yes, of course. I'm going to close everything, and we open Cycle. If you open Scipion, you have the list of the projects, and we are going to work with the project name Day 1, Alignment and Reconstruction. So I do click in the first one. And you find the project we are going to use. Okay, so in the left side of this project is all we did up to now. In the right side of this project, hanging from the import tilt series movies, is what I'm going to show you. The import of tilt series movies, Federico shown how to import the tilt series, and also Federico carried out a motion correction of the tilt series. Now I'm going to do something very similar, that is the tomogram reconstruction, but with splitting the tilt series in odd and even. What's the meaning of splitting the tilt series? Well, the movie, its image of the movie, its movie of the tilt series is composed by frames. So its image is composed by 6 frames. What we are going to do is to align those frames and split the frames in 2 subsets. One with the even frames and the other with the odd frames. So if I have 6 frames, I split those 6 frames in 3 odd and 3 even. And I will get 2 tilt series, one with the odd frames and the other one with the even frames. Okay? So how to do that? Well, we have imported the movies, and now we have to align the frames. Federico shown how to align the frames with motion cores. Alternatively, we can align the frames with flexalign. And then we open the flexalign, the input is a tilt series movies. That is the input. And in the advanced options, I can select split odd even frames. And I select it as yes. What will be the result? The result will be that flexalign, that is a protocol from xmipp to align a movie, will create 3 outputs. One is the motion corrected tilt series. The other one will be the motion corrected tilt series considering only the odd frames. And the third one will be the tilt series image with the even frames, also motion corrected. And the result is here. See that the parameters are almost the same than motion core. Motion core, I can also say the number of frames that I want to align, if I want to zoom them, and so on.
Okay, excuse me.
Yeah, tell me.
Which is the name of the input file?
The name of the input file, you can, well, the box is flexalign. You can find it here in Tilt Series Movies. xmipp Tomo Tilt Series flexalign. And the input is the movies. I only have 2 items. That is the imported Tilt Series movies.
One moment, please. Okay, thank you.
You're welcome.
Yeah.
And the important thing is that in advance, we are going to split in odd and even, because we want to get 2 Tilt Series. The one with the even frames and the second one with the odd frames. But also, flexalign will provide me the align with all frames. So the result will be 3 Tilt Series. You can see in the output the 3 Tilt Series: output Tilt Series, output Tilt Series even, and output Tilt Series odd. I can open any of them with IMOD viewer, and well, the Tilt Series is a bit large, so it takes a bit of time. Perhaps it's a bad idea to visualize it, but it will open. I wouldn't recommend you to open the Tilt Series in this case, because it's a big Tilt Series with 4,000 pixels. Okay, so now we have the Tilt Series. What we are going to do now is to align the Tilt Series. And we do exactly the same that we did before. Okay, it's true, if we want to do a perfect workflow, we have to first erase the X-rays and apply a dose filter. In this case, we directly went to the alignment. So we apply the realignment with IMOD. We generated Tilt Series with a binning 4, and we didn't use cumulative correlation. And we carry out the alignment of the Tilt Series with the full Tilt Series. I mean, the Tilt Series that was motion corrected, considering all frames. That is the output of flexalign. This one. So xmipp Tomo output on a stack of, yes, correct. The output of flexalign from xmipp Tomo is a stack with images. In particular, it will give me 3 stacks with the alignment of all frames, with the alignment of even frames, and with the alignment of odd frames. And now what we are going to do is to align the Tilt Series with all frames. Once we have the Tilt Series with all frames aligned, we can visualize the realignment with IMOD. This is small and should be fast.
Maybe a dumb question, but am I supposed to process now, or am I supposed to just listen? to the process?
I could recommend you that now just listen, because at the end what we are going to do is to launch Monotomo, and Monotomo takes time to compute. And you will not be able to compute it in short time. So I prefer that you will see how to do this in the. If you want to try it by your own, you have the.
No, so it's better just to listen now to the presentation and focus on what you are doing, right?
Yes. In the chat, you have the link with the. Here I'm opening the reconstruction. Oh.
Yeah, I already have opened that, but I was not sure whether I tried to redo what you already did in your file or just.
No, it's okay. Fede, can you put the Monotomo tutorial in the chat? Yeah, you will have the Monotomo tutorial in the chat now. Sorry. So this is what you are watching now is the pre-aligned till series. So of course you see some kind of jumps, but it's more or less pre-aligned. Also, you can see that this tomogram presents a high contrast, and it's because this tomogram considers was acquired with a Volta faceplate. So that's the reason why you see a lot of contrast and a lot of, let's say, detail of it. So once the till series are pre-aligned, we generated the fiducial model with the pre-aligned. The input of the fiducial model is the pre-aligned till series. The diameter, I'm not sure was this, yeah, probably. We put the number of fiducials and we compute it. So the result is 2 models with the fiducial. And finally, we apply the alignment. You can see the parameters. But in this case, we put both surfaces. We can put just one, and we apply binning 4. Just because in this course we said a lot of things, but one thing I would like to highlight, and that I consider that it's important, is that every time we align, we obtain 2 output. One with the till series that has the alignment matrix associated, but the alignment is not applied, but the information about the alignment is contained in the till series, but not applied. And the interpolated till series. The interpolated till series has the alignment applied, and also they can present a binning, because you want to be able of visualizing if the alignment is correct or not. Just here, if I open, it takes a little bit to open, but think that this till series is more or less small. It takes a bit of time to load it. But if I consider the full till series, will take more time. So that's the reason of binning and working with interpolated till series.
José Luis?
Yes.
Sorry. Could you repeat this fiducial model step again? And the other, yes. the last 2 ones, please?
Yes.
Thank you.
Well, we pre-align the till series, and now we generated the fiducial model. So we put the fiducial diameters, the number of fiducials, and if we want to find them in 1 or 2 surfaces, and if we want to apply a Sobel filter to find the edges of the fiducials and find the fiducials. So the input will be the pre-aligned till series, and the output will be a set of landmark models. It means a set of fiducial models. Because we have two tilt series, we will have two models, and this is them. And now this set of landmark models will be the input of the fiducial alignment. And we carry out the fiducial alignment. We put on both, on two surfaces, we can put just one if we want, and we apply a binning for because, and of course, generating the interpolated, because we want to be sure that our alignment was carried out properly. And due to our tilt series is large, almost 4,000, we apply a bin for to have a small set to check with the interpolated. This binning only affects to the interpolated tilt series. And the result is the set of tilt series and the interpolated tilt series. Also has the information about the fiducials and the coordinates of the fiducial value. The information that we want is the set of tilt series and the set of interpolated tilt series. And I highlighted that the interpolated tilt series are only used to visualize the alignment. That's why the binning is applied, because we want to load the result quickly. So now I'm open the interpolated tilt series with IMO. And yeah, the fiducials more or less is they move smoothly. So the alignment looks good. So now that the tilt series is aligned, we will work with the non-interpolated tilt series. Now we are sure that this alignment is correct. But here is the interesting part, because up to here, you can see how we process in column, as well as it happened here before, when we explained the fiducial alignment. But now, what we are going to do is to create two subsets. One, or two subsets, two reconstructions. One with the even image, and the other one with the odd image. Why we want to do that? Because we want to estimate the resolution of the reconstructed tomogram. And as well as it happened in single particle analysis, to estimate the resolution, we need a gold standard. We need two independent reconstruction. And in this case, the independent reconstruction come from the odd and even image. So there's one more thing. Sorry, I'm going to read the chat. Okay, good. I see Jorge is handling. Okay, so now we want to work with the odd and even image. But someone before asked about working with bin 1 instead of bin 4, and if we have to carry out again the fiducial alignment with bin 1. In this case, what we are going to do is to take the alignment information of the wall tilt series and assign that alignment to the even image and the odd image. So to do that, what we do is to find the assignment protocol. So let's press Ctrl F, and we can type assign. And here, Tomo tilt series assign alignment. we do double click. I move the window in order that you will find this. And I'm going to assign the alignment of what? Of the fiducial alignment, is this one, the set of tilt series, to the set of tilt series with the odd image, flexalign, odd image. You see? So now the information of the alignment of the wall tilt series is associated also to the odd image. This box is exactly this box. Is what we did here. So far, so good. And what I do with the odd image, I do the same with the even image. So in this case, I took the information of the fiducial alignment and I apply it to the even tilt series. So now I have the odd and the even tilt series with the information alignment. But the information alignment is associated to the tilt series, but is not applied to the tilt series. So if I see the tilt series, you will see, oh, bad idea because the tilt series is huge. Well, you will see that the tilt series is not aligned, but the transformation matrix is there. So we have to apply the transformation matrix, and we do that with IMOD. So,
José Luis, excuse me. Could you explain again why are we doing this? And is this explained in the document that you have sent to the chat?
Yes.
Okay. Thank you.
Well, what we are going to do, we want to estimate the resolution of the tomogram. To estimate the resolution, we need two reconstructions. In single particle, we have the two half maps. And what we are doing is to reconstruct two half tomograms. In this case, the half tomograms are named odd and even because we cannot split the set of particles into subsets. In this case, our set of particles are the tilt series. And if we split the tilt series in two subsets, we will have almost no image because our set of images is composed by 61 images. So it's a lot of loss of information if we split the set of images into two subsets. So instead of that, we take advantage of the frames. So we will split the set of frames in two subsets, the odd subset and the even subset. So splitting in frames, what we have is we still have 61 images per tilt series, but with the half of the frames. So the angular coverage, we conserve the angular coverage, but with a slightly lower signal-to-noise ratio. And what we did is to align the tilt series without losing information, and then to apply the alignment to the odd and even subsets. So what we did is to set the alignment to both subsets, and now we are going to apply the alignment. To apply the alignment, we go to tilt series, pre-process, and apply alignment to tilt series. And we select the tilt series that we want to apply, for instance, the even. So here, the protocol IMOD apply alignment tilt series takes the aligned tilt series even and apply the alignment to the tilt series. So I'm executing, but it's the same than this one. This part should run relatively fast. So what we have now? We have two tilt series, odd and even, that corresponds with the half of the information. And now we are going to reconstruct two tomograms, one with the even image and the other one with the odd image. And to do that, we use Tomo 3D. In the previous workflow, we've seen how to reconstruct with CIRT. You can see the protocol here, where my mouse is. And I take, the set of even tilt series, the CIRT, a thickness of 300, and execute. And the same with the odd tilt series. So in this point, what I have is two tomograms that I can open them with IMOD. So let's open the tomograms with IMOD. It will take a bit of time because the slices are 300, so this number have to go to 300. I'm sorry because I know this part of the course is a bit tricky and can confuse a little bit, but the most important is what we want to do. We want to estimate the resolution. To estimate the resolution, we need two reconstructions, each of them with the half of the data. In CryoEM, in single particle, are the half maps. Here are odd and even reconstruction. But they have to present the same alignment information. And all we did now is to be sure that both reconstructions have the same alignment information. That's why we align the tilt series and we apply the tilt series, the alignment information to the odd and the even subsets, and then we reconstruct the tomograms. So far, so good. Feel you free to ask because I know that this part of the workflow is tricky.
Okay.
Yes.
I'm going to resume these last steps. So we are trying to estimate the resolution, and that's why we are doing. We have split all the frames into all the images into sets, even and odd. Okay, and then we have to reconstruct the even set and the odd set.
Exactly.
In the same way as we have done before, right?
Exactly, correct.
Oh, okay, so the input will be the even set in one case and the odd set in the other case, right?
Exactly.
Okay, so we are doing right now that, right? We are doing that reconstruction, or we have done the reconstruction and you are doing another thing?
No. I'm doing exactly that. This is the reconstruction. What we are watching is the reconstruction of the even image.
Okay.
So that's why it looks like the wall, a normal reconstruction. I mean,
okay.
You see the cell, but this reconstruction only considers the even frames.
Okay, fine, thank you.
And in the right column, you have the same reconstruction or the same cell, but considering the odd frames.
Okay, what's the difference between even and odd frames?
Okay, you have its image in the TIL series. Let me close this. Here you have the TIL series. And, well, tells that you have 5 frames. Check that it says set of TIL series movies. I have 2 TIL series movies. It's composed by 61 build positions, the dimensions of the sensor, and each image is composed by 5 frames. So I'm going to take the first frame goes to the odd set. The second frame goes to even set. The third frame goes to the odd set, and so on. So I split those frames into 2 subsets.
Okay. Okay.
The ones with the odd position and the ones with the even position.
Okay, thank you.
And that's how we, considering the same alignment parameters, we obtain 2 tomograms, one with the even frames and the other with the odd frames. And then, to measure the quality, we can use local resolution monotomo. I'm going to analyze now because it takes a bit of time, because I already checked it, and it takes a bit of time, but meanwhile, I will explain. And now was absolutely quick. Good. Okay. This is the form of monotomo. Monotomo is a local resolution method to estimate the local resolution in electron tomography, the local resolution of the whole tomogram. It means it does not pretend to estimate the local resolution of a subtomogram. It considers the local resolution of the tomograms. So the input is the odd tomogram and even tomogram. Is the equivalent to the half maps in single particle. And it requires a resolution range. So what's my highest resolution and what's my lowest resolution? So in this case, we say the resolution of the tomograms are between 0, that means Nyquist, and 150, and then execute. So it's fully automatic. There are advanced parameters that you can say, okay, I want the resolution in steps of 0.5 Armstrong, or I can set to steps of 2 Armstrong, or whatever. But so it's fully automatic. And the result is what you saw here. So once the protocol ends, I do click on Analyze Results, and I select the tomogram I want. So the 1 or the 2. And appears the tomogram here. And I can select the range of resolution to show, for instance, from 30 to 140. And we may click on color resolution slices. And the result is my tomogram colored by the local resolution values that my tomogram has. You can, some interesting points of this is you can see in the slice 101, these circles are the fiducials. So you can see how the fiducials present a high contrast, has a border that is very clear. So the resolution of the fiducial is Nyquist, is the highest you can find. And you can see also the carbon edge. Here you have the carbon edge, and it presents Nyquist. And other interesting points are the borders of the cells. So you can compare this, if you remember, the shape of the tomogram was a big cell in the center, that is this cell. And also you could see how the cell inside has a lot of information. So then proteins inside, so you can see how inside monotomo tells that you have information of different resolutions. This can be very interesting to check the quality of your tomogram, to see if you have information of one point, or if you want to create mask, or if you want to segment your tomograms, and those kind of things. To open the result, because you are asking, just click on Analyze Result with the monotomo box selected, Analyze Result, the red button. And you select the tomogram. Here, select a tomogram. You may click on the magic rod and select the one you want information. You have to remove the TS /00 and put just 1. This is something that we will fix, but the first character must be a number. You have to remove any other characters. And then you may click on color slices. You can select also the resolution range between the highest and lowest. For instance, I put between 30 and 140. And if I may click now, you will see different colors, because before I put other color map. I put the color map Viridis. I put the Viridis color map because the rainbow color map, that is this one or jet, is color bias. There are some articles from mainly from meteorology or and weather prediction that say that the color map jet is present color bias in the interpretation, but it's widely used. So here you can see again the tomogram with colored by local resolution. And if you want, you can open the color tomogram in Chimera. I couldn't recommend you because it can take a lot of time now working with these machines. But if you have enough RAM memory, you can do it. And you would see some results like the ones that you have in the document. So here you can see the original tomogram, and you can see the tomogram colored by local resolution. And in Chimera, you can see in 3D colored by local resolution. That's why I say that can be used to carry out a kind of masking coarse segmentation or whatever. But it measures the local quality, nothing else. And that's all from my side. I don't know if you have questions. I regret that this part of is more tricky and can confuse you a little bit. I try to be as clear as possible. If you have doubts, I will be here these days, and you have the documents where all used parameters and information about how to carry out these pipelines are explained as much as possible, as much as we could. Now, if you have questions, how could one show the range between 30 and 80? Yes, of course. So here we go to analyze results. We select the tomogram. Let's set the first one. We need a number, so we put 1 here, and we put lowest, you say 30. So we put 30. And highest, we put 80. So we may click on color resolution slices, and it colors the range of resolution between 30 and 80. This is the pixels that are in that range. There are two important things. If I'm measuring 80 Armstrong, I need at least a box of 80 Armstrong around the voxel where I need to compute. Due to the pixel size is 8 Armstrong per pixels, I need at least 10 pixels to compute those 80 Armstrong. And also due to the low signal to noise ratio that tomograms present, the result it's so noisy. So it's only when we carry out tomogram imaging is when we obtain a high resolution or more normal resolution values. So monotomo will tells you the amount of spectral information of your tomogram. 10 voxels, sorry. And at least 10 voxels. 10 voxels could be the minimum. So that's another big problem in CryoEM, how local is local. Exactly. Exactly. If estimated 3 nanometers, I need at least 0. And I don't know if there are more questions.
This is a more general question from Christian. Maybe not addressed to you. I don't know if. So what are the possibilities in terms of visualizing membrane protein complexes in the plasma membrane?
Well, if you are asking if you can visualize the protein, the membrane protein with local resolution, your protein should be big. Otherwise, think what I said now. If I need 10 voxels to estimate the local resolution of 80 voxels, so I need large protein to be able of measuring properly the features of different sizes. One, 2 megadalton be visible? Probably. It's a big complex, but probably. $100 kilodaltons, probably it's the limit. It's something to check. To be honest, I didn't work with different sizes. the only thing I can tell you about local resolution is what I would expect, but we develop in this group the monotomo algorithm. We didn't use it in order to find complexes inside the tomogram. We just attempted to estimate the local quality of the tomogram. Yes, the missing wedge, you can visualize the missing wedge effect. In fact, it's something very interesting. If you visualize the y-axis, you would say you can visualize. Let me change the range, because let's put 140 to 30. So this is a side view of your sample. So perhaps in advance, if you may click in advance, you can select just one single slice. So let's put the slice 2000 and no.
You have 2,000 slices there, Vilas.
Oh, yeah. 400. It's interesting if you are able to find a region where you have a horizontal signal, the effect of the missing wedge, you will see that should disappear in the when you visualize the tomogram, you are not able to visualize horizontal lines when you see a side view of your tomogram because of the missing wedge. In other words, all planes parallel to the XY plane, you cannot visualize them in the tomogram. But local resolution in monotomo takes the resolution of whatever direction. If there's a direction with a high resolution, then we'll set the local resolution value to that point. So despite you have the missing wedge, you will be able to see horizontal lines because the local resolution perhaps goes in the horizontal plane along the y-axis or along the x-axis instead of the z-axis. So that's why you can see a behavior like this, where you can see a kind of a horizontal plane here or here. It's something perhaps complex to think about that, but if you think you can understand it. It doesn't matter. If there is a direction with enough resolution, then that pixel has a local resolution value. It doesn't matter the direction. It's set. More questions? If you have more questions about this, like this one about the missing wedge, we can go over them. You can ask me, and I can explain to you in a different room. And if there's no more questions, Federico was going to finally explain you how to reconstruct the tomograms with eTomo, because up to now we saw how to reconstruct the tomograms with in an automatic mode, launching the different protocols. But many of you probably would use eTomo to reconstruct tomograms with IMOD. So in Cypion, we also add that feature, and you are able to reconstruct with eTomo. So, Federico, and thank you. I will be here if you have questions.
Okay, hello back, everybody. Okay, it has been a long day. Courses officially ends in half an hour. And I'm sure as a first day, first day in the Cypion Tomo world has been a little bit tough for you. So, close the machine, please. So, first of all, I think rather than keep pushing more content, because maybe we are being a little bit optimistic on how much we can throw to you in a single day, I would like to make sure that there is no further questions. Anything you might from the whole day, anything you might want to address again, or maybe to I don't know, any doubts with any of the protocols of the steps we have performed today. And if not, if that's the case, just please unmute yourself or type in the chat. It would be a good moment now. And if not, and you are not very tired, we can make a little overview because I think I would rather explain a little bit and have it clear rather than to fool the rest of the time with too much content. So if there is no question, I might go off a little bit overview of what you can do manually inside Cypion with the eTomo interface. But first, if there is any question, please type and mute yourself. And if not, I will start with the workflow of eTomo. No. Okay, no questions. Okay. Then I hope you can see my screen now.
Yes.
Cool. Okay, so I am going to take to go over the already executed workflow, unless you think it's very interesting to go through all the steps of eTomo, but that maybe could take longer than half an hour. So I'll try to go for sorry, I'll try to go for an already executed eTomo version, and then we just close up the first day. I think it's more than enough content for you. So as we have seen in the morning, well, eTomo is the graphical interface of the IMOD software. So basically what we have done here is try to make the IMOD tools available, first of all, by its own, in case you want to solve a specific step in the tomography pipeline processing. And also we have made an effort for the automatization for batches of data, batches of till series. That's a good thing, because working manually, we have started seeing projects with huge data sets, hundreds of till series, and working manually may take even too much time for make the thing to make sense at the end. So that's very nice, but automatization has a problem, and it's that it doesn't always work as expected. there has been some questions flying around through the day about what do I do if I don't have fiducials or my fiducials are not properly detected, or what if my CTF is not good enough. Today we are not seeing CTF, it's day 3 content, and there is no manual CTF today, but you will see it. But for the rest of the steps, we are going to make a little bit entrance in what eTomo offers. So eTomo is the IMOD everything. Basically, everything is holded. All the protocols that you have seen from IMOD today, and even more, are holded inside the eTomo pipeline, the eTomo interface. And to execute it, sorry, and to execute it, it works exactly as any other protocol that we have seen through the day. You can search for it, Control F eTomo, and here it is. Or we can search it in the left menu. It should be both in the, I think, because you will see why, but it present both in the alignment and in the reconstruction. Could be actually everywhere, because almost any step can be solved, but because of how eTomo works, you might want to enter both with aligned series or not aligned series. This will make sense in a minute. Okay. So if I open the eTomo protocol, there is only 3 fields that might be filled out. First one is the input T series, is which set of T series you want to process. The second one is exclusion list that it allows to remove some views that you don't want to process, maybe for because in the acquisition something went wrong, whatever reason, maybe there is a view you don't want to process, so you can leave it out. And also as in the fiducial model generation, the fiducial markers diameter. Although any of these can be then changed inside the eTomo interface. So going to the already executed pipeline, or the already executed protocol that you have as a template, I'm going to use this one just for going a little bit faster and don't spend too much time. Basically, we can execute it as any protocol. This is the first one good thing about this. Interactive protocols inside Cypion can be executed anytime you want. So I can go into eTomo, execute or align 2 or 3 T series, and reconstruct the tomograms, and then go ahead and then come back for another 2 and make a new set of 5, and then a new set, and keep adding new information to the pipeline. In that case, as you can see, this is precisely this case. I have already executed one, and I have one that I haven't executed. I'm going to open the executed one just because we have 20 minutes, and I don't want to overtire you. So we just double click on the first one, and if it wants, that I don't know if it wants. Yes, give me a minute, please. Okay, let me try again, and if not, we can try with a non-process one, although I would prefer not to do so, just for the time. Okay, let's try with a new one then. Okay, there it is. I don't know why. Actually, this bothers me because I prefer to show you Okay. Anyway, then I think we will have to go through this. I will have to go a little bit fast, so if you can just sit back and follow me, it's more than fine. Because I don't know why it doesn't open to me. For any of you it's opening, then just follow it there because conceptually it's the same. So about eTomo, for those of you that maybe have a past with tomography, this is probably one of the most famous tools all around. It's, as I said, the whole IMOD software, basically. And it has its own underlying logic. So Scipion, it's very on the front. You have to think, if I want to interpolate, if I don't want to interpolate, if I want to bin, if I don't want to bin, if I want to combine or not to combine alignments, as in the assign alignment that you have seen. Here, this is more behind, and you do not need to be so much worried about. Basically, we have the whole pipeline we have seen today. We have from pre-processing to pre-alignment, fiducial model and fiducial alignment, tomograms, reconstruction and post-processing, and well, final cleanup step. So about the pre-processing, as we have seen in our the first thing we have done today, right? The X-ray removal. Here you can find your X-rays. You can create a X-ray cleaned stack and view it, use it if you like it, and some other more manual tools. I'm going to skip this step. And here we go to course alignment, which is our cross correlation pre-alignment inside Scipion, which would be this box here. And oh, sorry. And why this is not here? Okay. And what I'm going to execute just to let's see how fast it is. But okay, it will take a long time. Okay, then I will just have to. Wow. Okay. Okay, so this will be our first step, the pre-alignment. Once we have our pre-alignment stack, which this is a step that usually is not very conflictive. So here is maybe where the automatic tools are more functional. We go to the fiducial model generation, and here is where eTomo is more powerful. Basically because it will bring up some options that or are not available inside Scipion yet, or it doesn't make that much sense, or doesn't make that much sense, that maybe are more a manual thing, and at the end you will have to deal with going each till series one by one, instead of processing it in batches. There was a question this morning about what happens if I don't have fiducial markers. We do not have fiducial tools yet, fiducial-less tools yet in Scipion, but here is one. So you can use tracking to make patch tracking to make fiducial model. Basically, what it does is it looks for contrast features, the high contrast features that allows you to detect all of them in all the images as a good function with a fiducial or a gold bit. Here, the fiducial model generation in IMOD is done in 2 steps that are covered inside Scipion and are merged in just one single protocol, which would be the fiducial model generation protocol. A first one, which would be the fiducial model generation. Try luck with this. And a second one, or a seed model, and a second one which is track bits. So seed model, what it does basically is detect gold bits in the center of the series. Here there is really a lot of options. You can you select the density, if you want to apply any filter, the density, the select the gold bits by density or by number, like how many bits I want, the select to bit surface that we have talked before. You can even add bits manually to a pre-selected or a pre-generated seed model, and you can also generate your own seed model by hand. In my experience, with conflictive series, this is one of the steps that it's more powerful, or it's more likely to fail in automatic compared with the results you can obtain manually, which is detecting the gold bits at the beginning. The second step, which is tracking the bits, which is basically looking for those bits you have selected around the whole series, it's more or less stable. But detecting those first gold bits, it's in my experience at least, where most of the cases the algorithms fails. And apart from that, eTomo, once the fiducial model is generated, it gives you the option to fix it, to be even more precise, to correct for maybe you have detected the gold bit, but not exactly in the center of the gold bit, and you want to make sure that every time the gold bit is in the center. All these kind of things can be refined manually. The problem, it takes time. It's not an uncomfortable GUI. It's not an uncomfortable graphical interface. Everything is it's very detailed, it's done with a lot of love, that's for sure. But what is true is that at the end, it takes time. More if you are not an expert like me. If you are super used to it, maybe you can go faster. So once you have your fiducial model, you would go to fiducial alignment. This is a more straightforward step. But basically, considering the fiducial model, eTomo is looking for the proper alignment, detecting the gold bits, as we have done here. So basically, this conceptually is the same step than the fiducial alignment that we have done before. The thing is that, well, there is, again, as you can see, eTomo is super intensive in options, and sometimes not even all are exposed. Here they are, but for example, here you think it's more less simple, and if you start deploying all the options, it gets very complicated. But I mean, if you're an expert, I'm sure you can take profit of this. Apart from the alignment variables, I don't want to spend too much time on this, but it will allow you to solve for different movements of the series. And again, the more things you want to solve, the more time it takes, and you are more likely to fail. For example, I don't know, imagine I want to solve for all rotations and all the magnifications and all the tilt angles and all the formation of the images and everything to perfectly align. If you do it, it will be great, and you will have the most refinement alignment possible. But it will take time, and I'm not saying it will fail. It perfectly can go fine, but it's more probable you to fail if you want to refine harder your results. Once it's done, there is an interesting step here about tomogram positioning. This is something that is not fully solved manually, basically because it's very hard to solve manually. Automatically, it's very hard to solve. There are some new tools that we have to look at, but we do not have automatic positioning tools yet in Sapien. But basically, what these tools allows to you is to fix the region you want to reconstruct. So in our reconstructions, we just set the thickness of the sample, but here you will have the option of rotate a little bit your region, or move it upwards, or move it downwards, but looking at a sample tomogram. That's why here it says create sample tomogram. In the automatic step, you have to do it blindly, and for all the series applying the same approach, or the same offset values. So that's why this is another step where you can take advantage of manual approaches rather than the automatic one. Once you have positioned your once you have positioned your tomograms, now you can go for the final alignment. Final alignment is basically what we have seen the rest of the morning. This 2D filter is the dose filter we have applied at the beginning. The CTF is what you have seen with Jose Luis Vilas, but it's correcting the CTF. There is something we haven't talked about today, although we have the option inside Cypion in the fiducial alignment. We have here the option of erasing the gold bits. We haven't done it, but the option is there. And here the option is available too. This is basically done to avoid artifacts generated by the gold bits because of they are very dense black dots. And again, as you see, you have to deal also with binning values, etc. But basically, this is like the rest of the TIL series pipeline you have seen today, condensed in this step. And once you have your final alignment, you can reconstruct. And here you may ask yourself, okay, but if I pre-aligned or if I erased, if I align with gold bits, what happens now? Why I'm applying the 2D filter? Okay, eTomo is doing everything on your behind. It holds all information as a whole one environment, and for those operations that it's better to go for the raw images, it will go, and for those who it doesn't. But you won't have to notice about it. You don't have to decide it. While Cypion, for some of the operations, you need to be aware of what is the input that you are taking to your protocol. And once you have done it, as you have seen today, tomogram reconstruction. Here you have the seared option. We do not have it yet in Cypion. You have the weighted back projection also, and again, all the options that and again, and I insist with this, is very intensive in options. So this is not even all; these are all. Okay, things might get very messy inside eTomo. One of the things that in my feeling, at least as a non-professional professor of data, sometimes it may get a little bit too overwhelming at the beginning, at least to use everything, be sure what you are doing, if something makes sense or not, might be hard. If, for example, you have the seared like filter that you have seen in the previous one, and just at the end you can you can post-process your tomogram, you can rotate the output tomogram, you can range the values or scaling the values, several options. And that's pretty much all. So, and well, there is a final step of cleaning intermediate files just to save some space in disk. So that's pretty much all. I'm sorry we have to see this in just 10 minutes, but I think it has been way too much for today. Maybe we have been a little bit optimistic of what we can handle in a day, but I think that although it has been only 10 minutes, it makes sense for you. It makes sense for you to know that you have also these options inside. And the good thing about this is that whatever you do inside eTomo, so we close it, and Cypion will handle everything and will interpret the outputs generated. You don't have to tell Cypion which outputs you have generated or not. It will do it by its own. You don't have to worry about that. And once you are finished and you close this window, okay, we haven't generated any output in this case, but in the previous execution you have, all the previously generated outputs are there. So imagine that for any reason you have reconstructed and you have in your beautiful post-process tomograms, but you want to go back and try with JJSoft Tomo 3D. But then you can take your aligned images and try with it. So it's still compatible with the whole environment of Cypion. You don't have to decide between eTomo approach and an automatic approach. Everything is still compatible. It's just that here you will have to go one by one. If you have 100 series, you will have to go one by one 100 series and process everything. But once you do it, everything is still completely compatible with the rest of the environment. And as I said, you don't have to be worried about what I generated or what I not. You just do your job inside eTomo, and Cypion, all the information you generated, it will do its best to offer you inside the environment, whatever it is, a pre-aligned series or a fully post-processed tomogram. Well, besides that, that's pretty much all. That's our first day. I know it has been hard. I know there is a lot of information for a first day in tomography, but it's a 4-day course, and we have to take as much as we can. So I hope it hasn't been a little bit overwhelming for you, but it was. We really like to hear from you what you think. If you would rather keep it more simple and going slower, we are glad to hear. It's our first workshop in tomography, so I mean, first times is for our first times, but I just hope that you get a good overview of the options you have and the things you can do, and think that you have half of the workflow almost done. So reaching the tomogram sounds like the beginning, but although it's the beginning, it's a significant percentage of the processing. So I hope you find it interesting. That's all. We do not have anything more to tell you. I hope we have done it. We did our best, right? And then if now you have any question, doubts, any comment on particular general things, more theoretical things, more sapient things, we have now some room for questions if you want. And if not, we are on a scheduled time, believe it or not. so I really hope you found it at least forming and interesting. Thank you very much.
I would like to thank Fede and Vilas for this effort and this day. I agree it's been a bit dense, but there's no other way to do it. And one more important thing, if you've seen that there will be a survey at the end of the course, so take good notes of what can be improved. And if there's something that can be improved right now or for tomorrow, just let us know, because maybe there are things we are trying to get the machines up and running and all that. But
it's not really. Sorry.
Yeah, go ahead.
It's not really course-wise, but I was confused about the time when it started today, because at one point it was mentioned 9:30 CEST, and on I don't know, some on the same document, but later on said CET.
Yeah, well, probably, yeah. It's not summertime, so yeah.
Yeah.
Probably we got, or someone got confused about we added the EDS. Yeah. Sorry about that. It will be 9:30 CE time, right?
Yeah.
Not summertime.
Perfect.
That's it.
Way better.
Sorry about that.
Thank you very much.
But thank you very much for this good introduction and description.
Thank you.
You're welcome.
So then, see you tomorrow then. Thank you, Fede.
No
Thank
question.
you, everyone.